There is a place on this planet where the water runs so deep, so dark, and so silent that sunlight has never once touched the seafloor beneath it. A place where mountains taller than anything standing above the surface of the land rise in complete and total darkness. A place where creatures have evolved armor made of iron, where ancient continents lie buried beneath the waves, where the very gravity of the earth behaves differently than anywhere else on the planet. This place is not some distant corner of the solar system. It is not a theoretical landscape imagined by scientists in laboratories. It is right here, on our own world, covering nearly 70 million square kilometers of the southern hemisphere, stretching from the frozen edges of Antarctica all the way to the warm coastal shores of southern Asia. It is the Indian Ocean, and despite centuries of human civilization flourishing along its coastlines, despite the thousands of ships that have crossed its surface, despite everything we believe we know about our own planet, the Indian Ocean remains, to this day, one of the least understood, least explored, and most profoundly mysterious regions on the face of the Earth. Please let us know in the comments where you are watching this documentary and what time you are watching it. And be sure to subscribe to the channel for future videos. What you are about to witness over the next 2 hours is not a simple survey of ocean facts. This is a deep dive in every sense of those words into a world that science is only beginning to comprehend. We are going to travel through geological time, descending through layers of sediment that hold the memory of ancient climates, ancient extinctions, ancient worlds that no longer exist in any form we would recognize. We are going to stand metaphorically on the edges of hydrothermal vents where superheated water blasts upward from cracks in the seafloor at temperatures that would dissolve metal, creating towers of mineral deposits that rise like Gothic cathedrals in the permanent midnight of the deep ocean. We are going to encounter life forms so strange, so completely alien in their biology and their behavior, that they challenge every assumption we have ever made about what it means to be alive. And through all of it, we are going to keep asking the same fundamental question, a question that becomes more urgent the deeper we go, the more we discover, the more we understand about how little we actually know. How is it possible that we have mapped the surface of Mars with greater precision and detail than we have mapped the floor of this ocean? How is it possible that we have sent machines to the edges of the solar system, that we have looked back through time at the earliest moments of the universe itself, and yet we still cannot tell you with confidence what lies at the bottom of vast stretches of the Indian Ocean? The answer to that question is complicated and beautiful and humbling, and it begins, as all great ocean stories begin, not with water, but with rock. To understand the Indian Ocean, you have to first understand that the ocean itself is not a permanent feature of this planet. Nothing about the surface of the Earth is permanent. The continents are moving right now, grinding against each other, pulling apart from each other, sinking beneath each other at rates so slow that no human being will ever perceive the motion directly. But over millions of years, those movements have rearranged everything. They have opened ocean basins and closed them again. They have pushed mountain ranges up from flat plains and eroded those mountains back down to nothing. They have created and destroyed entire geological worlds with a patience and indifference that is almost incomprehensible to creatures who live for decades rather than for hundreds of millions of years. The Indian Ocean, as it exists today, is a relatively young feature of the planet's surface. Geologically speaking, it is a newcomer, a body of water that began forming roughly 180 million years ago when the ancient supercontinent known as Gondwana began to break apart. Gondwana was a massive landmass that contained what we now recognize as Antarctica, Australia, the Indian subcontinent, the Arabian Peninsula, Africa, and South America, all pressed together into a single enormous continent that would be unrecognizable from the perspective of anyone standing on the Earth today. And then Gondwana began to fracture. The process was not sudden. There was no single moment of catastrophic breaking. Instead, the rifting was gradual, driven by the slow churning of the mantle beneath the crust, convection currents of semi-molten rock that have been operating continuously for billions of years, dragging the rigid plates of the Earth's outer layer around the surface like passengers on an impossibly slow conveyor belt. As Gondwana broke apart, gaps opened between the separating pieces of crust. Those gaps filled with seawater. And over tens of millions of years, those gaps widened and deepened, and eventually became the ocean basins we know today. The Indian Ocean is the scar left behind by that ancient breaking apart. It is the water that filled the void left when the Indian subcontinent tore free from what is now Antarctica and began its extraordinary journey northward, a journey that would eventually carry it into a collision with the Asian landmass, and over tens of millions of years, push up the Himalayan mountain range as a result of that slow-motion catastrophe. The Indian Ocean, in other words, is intimately connected to some of the most dramatic geological events in the history of this planet. It did not simply appear. It was created by forces of almost incomprehensible power, operating over timescales that dwarf human history the way human history dwarfs the lifespan of a single mayfly. But here is where the story becomes genuinely astonishing, because the breakup of Gondwana did not proceed cleanly. When continents tear apart, they do not always leave behind perfectly organized fragments. Sometimes pieces get left behind. Sometimes chunks of ancient continental crust get stranded in the middle of what becomes ocean, carried away from their original position, submerged beneath layers of ocean sediment, lost to any casual observation for hundreds of millions of years. And in the Indian Ocean, we now know that this is exactly what happened. The island of Mauritius sits roughly 2,000 kilometers off the eastern coast of Madagascar in the southwestern Indian Ocean. It is a volcanic island, formed, like Hawaii, by a hotspot in the mantle that pushed magma up through the ocean crust to build a mountain that eventually broke the surface of the water and became land. It is, by all appearances, a purely volcanic feature. The rock that makes up most of the island is basalt, the dark, dense rock that forms when volcanic magma solidifies. There should be nothing on or in Mauritius that dates back more than a few million years, because that is roughly how long ago the volcanic activity that built the island occurred. And yet, in 2017, a team of geologists studying the beaches of Mauritius made a discovery that fundamentally changed our understanding of the geological history of the Indian Ocean. They found zircon crystals in the beach sand, tiny, almost invisible crystals that are remarkable for one specific reason: they are almost indestructible. Zircon crystals can survive almost any geological process. They can be carried in magma, incorporated into rock, eroded out of that rock, transported by water, and deposited in sediment, all while preserving within their crystal structure a precise chemical record of when they originally formed. And when the scientists dated the zircon crystals they found on the beaches of Mauritius, they got a result that initially seemed impossible. The crystals were approximately 3 billion years old. 3 billion years, in a place where the youngest rock on the surface is a few million years at most. There was no way, under any normal geological scenario, that 3 billion-year-old crystals could have ended up on the beach of a young volcanic island, unless those crystals had been carried up from somewhere much deeper, somewhere beneath the volcanic rock, somewhere that the magma had passed through on its way to the surface. The only explanation that made sense, the only geological scenario that could account for the presence of those ancient crystals in that specific location, was that beneath the volcanic rock of Mauritius, buried under layers of basalt that were laid down over millions of years of volcanic activity, there is a fragment of ancient continental crust, a piece of a continent that no longer exists as a landmass. A ghost of Gondwana, preserved beneath the Indian Ocean, invisible from the surface, detectable only because volcanic activity accidentally brought traces of it back up into the light. The scientists named this lost continental fragment Mauritia. And since its discovery, evidence has emerged suggesting that Mauritia may not be alone, that the floor of the Indian Ocean may conceal multiple fragments of ancient continental crust, scattered remnants of the great landmasses that once existed before Gondwana broke apart, preserved in the darkness beneath billions of tons of seawater and hundreds of millions of years worth of accumulated ocean sediment. This discovery is not a minor footnote in geological science. It is a fundamental revision of our understanding of how this ocean formed, how the continents separated, and how much of Earth's geological history is still hidden from us, not on some distant world, not in some inaccessible corner of space, but right here, beneath one of the planet's major ocean basins, waiting to be found. If Mauritia exists, and the evidence strongly suggests that it does, then the geological map of the Indian Ocean floor is far more complex, far more ancient, and far more surprising than anyone had imagined even a decade ago. But the geological surprises of the Indian Ocean do not end with lost continents, not even close. Because somewhere in the northern portion of the Indian Ocean, there is an anomaly in the Earth's gravitational field so extreme, so unusual and so difficult to explain that scientists have spent decades trying to understand it, and in many ways that understanding is still incomplete. Gravity, as we experience it on the surface of the Earth, is not perfectly uniform. The Earth is not a perfect sphere, and its interior is not uniformly dense. Regions of the Earth's interior that are denser than average exert a slightly stronger gravitational pull. Regions that are less dense exert a slightly weaker pull. These variations in gravitational pull across the surface of the planet are small, far too small to be felt by any human being going about their daily life. But they are measurable, and they are scientifically significant because they reveal information about the structure and composition of the Earth's interior that cannot be obtained in any other way. In the Indian Ocean, south of the Indian subcontinent, there is a region where the gravitational field is measurably weaker than it is anywhere else on the planet. This region has become known, informally but evocatively, as the Indian Ocean gravity hole. It covers a vast area, roughly 3 million square kilometers, and within it, the gravitational pull of the Earth is significantly lower than the global average. So much lower, in fact, that the sea surface itself is measurably lower in this region than it would be if gravity were uniform. The water is literally not being pulled as hard toward the Earth's center, so it sits slightly lower than the surrounding ocean. For decades, scientists studied this gravity anomaly and struggled to explain it. Normal explanations for local gravity variations, variations in the thickness or density of the crust, variations in the distribution of rock types in the upper mantle, did not seem sufficient to account for something this large and this extreme. The gravity hole seemed to require an explanation that reached much deeper into the Earth's interior, into regions of the mantle where our understanding of what is happening physically and chemically is still very limited. In recent years, a new hypothesis has emerged that may finally explain the Indian Ocean gravity hole. Using sophisticated computer models of the Earth's mantle and its long-term behavior, a team of geoscientists proposed that the anomaly is connected to the ancient breakup of Gondwana and the tectonic history of the region. Specifically, they suggested that as the ancient Tethys Ocean, the precursor ocean that existed before the Indian Ocean formed, was being subducted beneath the Asian continent hundreds of millions of years ago, it created disturbances in the flow of the mantle that propagated downward and outward over geological time. These disturbances, combined with the effects of a plume of unusually hot and therefore less dense mantle material rising beneath the region, created a zone of anomalously low-density material in the mantle beneath the Indian Ocean that persists to this day, and it is this low-density material beneath the seafloor, this ancient scar in the mantle left by a geological event that happened hundreds of millions of years ago, that is responsible for the gravity hole. If this hypothesis is correct and the computer modeling results are compelling, then the Indian Ocean gravity hole is essentially a fossil. Not a fossil in the conventional sense of a preserved organism, but a fossil in the geological sense, a preserved record of an ancient process, locked into the structure of the planet's interior, detectable only because of the subtle influence it has on the gravitational field at the surface. It is a ghost of an ocean that no longer exists, embedded in the fabric of the Earth itself, whispering its ancient history to those who know how to listen. The floor of the Indian Ocean is not flat. This is perhaps the most important single fact to understand before beginning any serious exploration of what lies beneath the surface of this water, because the mental image most people carry of the seafloor, a flat, featureless plain of mud stretching away in all directions, is as far from reality as any image could possibly be. The seafloor of the Indian Ocean is a landscape of staggering complexity and variety. It has mountains and canyons, plateaus and trenches, vast plains and towering ridges. It has features that dwarf anything visible on the land surface of this planet, and it has features so subtle and delicate that they can only be detected with the most sensitive scientific instruments available to us. The most prominent structural feature of the Indian Ocean floor is the system of mid-ocean ridges, underwater mountain ranges that mark the boundaries between the tectonic plates that make up the ocean floor. These ridges are where new ocean crust is being created. As the plates on either side of a ridge pull apart from each other, magma from the mantle below wells up through the gap, solidifies, and adds new material to the edges of both plates. The process is slow. The plates in the Indian Ocean are generally moving apart at rates of a few centimeters per year, but it is continuous, and it has been operating for tens of millions of years, gradually expanding the ocean basin and carrying the old ocean crust away from the ridges and toward the continents on either side. The Indian Ocean has several major ridges. The Central Indian Ridge runs roughly north-south through the center of the ocean basin, connecting in the south with the Southwest Indian Ridge and the Southeast Indian Ridge at a point known as the Rodriguez Triple Junction, one of the most geologically complex spots on the ocean floor, where three separate tectonic plates meet at a single point, and where the geometry of plate tectonics produces some of the most unusual and dynamic geological conditions anywhere on the planet. The Southwest Indian Ridge is particularly interesting to scientists because it is one of the slowest spreading ridges on Earth. While some mid-ocean ridges spread apart at 10 to 15 centimeters per year, fast enough by geological standards to produce smooth, broad ridge structures, the Southwest Indian Ridge spreads at less than 2 centimeters per year. This extremely slow spreading rate has profound consequences for the structure of the ridge and the nature of the seafloor it produces. At slow-spreading ridges, the magma supply from the mantle is insufficient to completely fill the gap between the separating plates with new volcanic material. Instead, the mantle rock itself, a type of rock called peridotite, is sometimes dragged up to the surface, unmelted, and exposed directly on the seafloor. This creates a seafloor geology that is unlike anything produced by faster-spreading ridges, a mosaic of different rock types, with volcanic basalt interspersed with exposures of deeper mantle material, all cut through by fault systems that produce dramatic cliff faces and valley floors. The Southwest Indian Ridge is also geographically remote in a way that makes it particularly difficult to study. It runs through some of the most isolated waters on Earth, far from any continental coast, far from any established shipping routes, in a region where weather conditions are frequently extreme, and where the logistics of mounting a scientific expedition are correspondingly formidable. Many stretches of the ridge have been visited only a handful of times by research vessels, and some sections have never been visited at all. What the unsurveyed sections of this ridge look like, what geological features they contain, what mineral deposits might be accumulating there, what life forms might be inhabiting the vents and cracks in the rock, all of this remains almost completely unknown. And this is where the concept of the deep ocean as a genuinely unknown frontier becomes most vivid and most urgent. We use the phrase unexplored territory loosely in everyday language, applying it to things that are merely unfamiliar or understudied. But in the case of the deep Indian Ocean, the phrase is literal. There are sections of the seafloor, entire mountain ranges, vast stretches of abyssal plain, kilometer-deep trenches, where no human-made instrument has ever operated, where no camera has ever transmitted an image, where no sediment sample has ever been collected, where no measurement of any kind has ever been taken. These are not places that are merely poorly understood. They are places that are, in the most direct and unambiguous sense of the word, unknown. Consider what we mean when we say that the seafloor of the Indian Ocean is unmapped. Modern bathymetric maps of the ocean floor are compiled from two main sources: satellite altimetry measurements of the sea surface, which can detect the subtle bulges and depressions in the ocean surface caused by underwater topography, and thereby provide a rough estimate of what lies beneath, and ship-based sonar measurements, which send pulses of sound downward through the water and measure the time it takes for those pulses to return from the seafloor, thereby providing a much more precise picture of the bottom topography. Satellite altimetry can cover vast areas quickly, but its resolution is limited. It can detect features that are several kilometers across, but it misses anything smaller. Ship-based sonar provides much higher resolution, but covers ocean floor only in the narrow swath directly beneath the ship's track. The result is that our current bathymetric map of the Indian Ocean is essentially a composite. Large areas mapped by satellite to low resolution, with narrow strips of higher resolution sonar data scattered across it where research vessels have happened to travel. Between those strips in the vast unmapped spaces, the actual topography of the seafloor is largely a matter of inference and estimation. We know in general terms that there is a ridge here, a plain there, a trench somewhere in this region. But the details, the exact depths, the specific textures of the seafloor, the locations of individual seamounts, the precise dimensions of geological features, those details are simply not known over vast stretches of the ocean floor. This is not, it should be said, a matter of technological limitation alone. The tools needed to map the deep ocean floor with high resolution exist. They are expensive and the process is slow. A research ship moving at typical survey speeds can map roughly a strip of seafloor about 15 kilometers wide, and the Indian Ocean is roughly 10,000 kilometers across at its widest point. But it is physically possible to produce a comprehensive, high-resolution map of the entire Indian Ocean floor. What has prevented this from happening is a combination of cost, logistical difficulty, institutional priority, and the simple fact that for most of human history, what lies at the bottom of the deep ocean has been considered less immediately relevant to human concerns than what lies on the surface or in the shallow coastal waters. That view is changing. Slowly, expedition by expedition, sonar swath by sonar swath, the detailed topographic picture of the Indian Ocean floor is being assembled. And with each new survey, with each new set of data, the picture that emerges is more complex, more interesting, and more important than anyone previously imagined. Let us go deeper now. Let us descend from the surface, through the sunlit zone where photosynthesis drives the base of the ocean's food web, down through the twilight zone where light fades to a dim blue glow and then to nothing, into the midnight zone where the darkness is absolute and the pressure is measured not in atmospheres but in hundreds of atmospheres, where the weight of the water column above pushes down with a force of several thousand kilograms per square centimeter on everything it contains. The descent is not a metaphor. It is a physical reality that defines everything about life in the deep ocean. For every 10 meters of depth, the pressure increases by approximately 1 atmosphere, roughly the equivalent of the entire weight of the air column above the ocean's surface. At a depth of 1,000 meters, the pressure is approximately 100 times what it is at the surface. At 3,000 meters, roughly 300 times. At the bottom of the deepest trenches, where depths can exceed 10,000 meters, the pressure is more than 1,000 times the pressure at the surface. It is a crushing, annihilating force by any human standard, and yet life thrives in it. Life has adapted to it in ways that are still being discovered, still being understood, still being cataloged and analyzed by scientists working at the very frontiers of biological knowledge. The twilight zone, roughly 200 to 1,000 meters depth, is a region of profound importance in the ecology of the open ocean. It is here that many of the organisms that feed near the surface during the night descend to hide from predators during the day. The daily vertical migration of zooplankton and small fish between the surface and the twilight zone is one of the largest and most regular animal movements on Earth, a pulse of life going up and down with the rhythm of the sun that has been operating continuously for hundreds of millions of years. This migration carries organic material from the surface, where photosynthesis creates new biological matter, downward into the deeper ocean, where it provides food for a complex community of organisms that live in the permanent dimness. The twilight zone is also a region of intense scientific interest because it plays a crucial role in the global carbon cycle, sequestering significant quantities of carbon dioxide absorbed from the atmosphere by surface ocean organisms and carrying it down into the depths where it may remain for centuries or millennia before returning to the surface. Below the twilight zone, below 1,000 meters, is the midnight zone, the bathypelagic region, where no light of any kind penetrates from the surface above. In this zone, life must subsist entirely on what drifts down from above. The euphemism scientists use for this is marine snow, the continuous, gentle fall of organic particles from the water above, dead organisms, fecal pellets, mucus, fragments of shell and scale. It sounds poetic, and in a certain sense it is. But it is also sparse. The deeper you go in the open ocean, the less food is available, and the more spread out and isolated the communities of organisms that depend on it become. Life in the deep midwater of the Indian Ocean is real and varied. There are fish here, gelatinous creatures, crustaceans, all manner of adapted organisms, but it is thinly distributed, spread across an enormous volume of water, operating at a pace and on an energy budget that is difficult to comprehend from the perspective of organisms that live in the productive, sun-energized world above. And then there is the seafloor itself, the benthic zone, the bottom of the ocean. And here something completely different happens. Something that, when scientists first discovered it in the late 20th century, was so unexpected, so contradictory to every established understanding of how ocean life worked, that it required a fundamental rethinking of the basic principles of biology. In 1977, a research submersible called Alvin was exploring the Galapagos Rift in the Pacific Ocean, a spreading center where tectonic plates are pulling apart and new ocean crust is being created. Scientists on that expedition were searching for, among other things, hydrothermal vents, cracks, or fissures in the seafloor through which water heated by the magma below the crust might emerge. They had theoretical reasons to believe such vents should exist, and previous expeditions had found hints of their presence through anomalies in the temperature and chemistry of the deep water. But no one had ever actually seen a deep-sea hydrothermal vent. No one knew for certain what one would look like, and no one, not a single scientist involved in the expedition, not a single oceanographer anywhere in the world at the time, had any expectation of what would be living around it. When Alvin's cameras captured the first images from the seafloor around the Galapagos Rift vents, the reaction of the scientists aboard was one of pure, undiluted astonishment. Around the vents, in the complete darkness of the deep seafloor, in water that was away from the vents themselves, just above freezing, there was life. Not trace amounts of microbial life, not a few scattered organisms clinging to the rocks. There was a riot of life. Dense communities of organisms, some of them large by any ocean standard, covering the seafloor around the vents in a profusion that seemed impossible in a place this remote from the sunlit surface that drives all ocean productivity. There were giant tube worms, 2 meters long or more, swaying in the gentle currents of the vent effluent. There were clams the size of dinner plates. There were crabs and fish, and communities of smaller organisms so dense that they carpeted the seafloor in layers. How could this be? The scientific community's first, bewildered question was the right one, and the answer that emerged over the following years of intensive research was one of the most important discoveries in the history of biology. These communities were not dependent on photosynthesis. They were not deriving their energy, directly or indirectly, from sunlight. They were thriving in a place where sunlight had never reached and could never reach, and they were doing so because of an entirely different form of primary production, a process called chemosynthesis. Chemosynthesis is the biological conversion of chemical energy into organic matter. In the case of hydrothermal vent communities, the chemical energy comes primarily from the reaction of hydrogen sulfide, a compound that is toxic to most life forms, but that is produced in large quantities by the geochemical processes occurring in the hot rock around vent systems, with oxygen dissolved in the seawater. Certain microorganisms have evolved the biochemical machinery to catalyze this reaction and use the energy it releases to fix carbon dioxide into organic compounds, just as plants fix carbon dioxide using the energy of sunlight. These chemosynthetic microbes form the base of an entire food web, a food web that operates completely independently of the sun. The discovery of chemosynthetic ecosystems around hydrothermal vents was revolutionary not just for oceanography, but for biology as a whole. It demonstrated that life does not require sunlight. It demonstrated that the energy needed to drive biological processes can come from the chemical energy stored in the bonds of inorganic molecules. And it expanded the theoretical range of environments in which life might exist, not just on Earth, but anywhere in the universe where liquid water and the right chemical conditions occur together. The icy moons of distant planets, previously dismissed as too cold and too dark to support life, suddenly became candidates for habitability. The entire understanding of what it means for an environment to be habitable shifted in response to what was found around those vents at the bottom of the Pacific Ocean. And the Indian Ocean has its own hydrothermal vents, of course it does. It has its own mid-ocean ridges, its own spreading centers, its own system of cracks and fissures through which mantle-heated water emerges onto the seafloor. The Indian Ocean vents were discovered later, explored less thoroughly, and in many cases remain far less studied than their counterparts in the Pacific and Atlantic. But they are there, and what has been found at those vents is every bit as extraordinary as what was first discovered nearly half a century ago in the Pacific. The Indian Ocean's hydrothermal vents are found primarily along its mid-ocean ridge system, along the central Indian Ridge, the southwest Indian Ridge, and the sections of ridge in the southern portions of the basin. Each vent field is in some ways unique, a product of the specific local geology, the specific chemistry of the fluids emerging from below, the specific temperature profile of the emerging water, and the specific community of organisms that has colonized it. But all of them share certain fundamental characteristics that define the vent environment: extreme heat, chemical richness, darkness, high pressure, and the extraordinary life that has evolved to exploit these conditions. The superheated water that emerges from the most extreme type of hydrothermal vent, the black smoker, can reach temperatures exceeding 400 degrees Celsius. This is far above the boiling point of water at the surface, and yet the water in a black smoker does not turn to steam, because the immense pressure of the overlying water column prevents it from making the phase transition. It remains liquid, barely, but it is liquid at a temperature that would instantly destroy any complex organic molecule that came into contact with it. The black smoker fluid is also extraordinarily rich in dissolved minerals, sulfides of iron, copper, zinc, and other metals that precipitate out of solution when the superheated vent fluid meets the cold ambient seawater, forming the dark plumes of particulate material that give black smokers their name, and gradually building up the chimney like mineral structures, some of them tens of meters tall, that are among the most striking visual features of the vent environment. The mineral structures built by hydrothermal venting are not just geological curiosities. They are active, dynamic formations that grow and change on timescales of years to decades. New mineral material is deposited continuously as vent fluid precipitates out its dissolved load on contact with colder water. The chimneys grow taller, more elaborate, sometimes branching and merging into complex three-dimensional structures that look, in the beam of a submersible's lights, like the ruins of some impossible architecture, spires and arches and columns and walls of sulfide mineral, all of it built by chemistry rather than by any biological or human agency, all of it colored in shades of black and gray and yellow and white by the different mineral compounds of which it is composed. Around the chimneys and on the surrounding seafloor, the community of life is dense, diverse, and, to eyes accustomed to the relatively familiar world of surface ocean ecosystems, deeply strange. The key to understanding this strangeness lies in the microbiology. At every vent, the foundation of the ecosystem is a community of chemosynthetic microorganisms, bacteria and archaea, that have evolved the biochemical machinery to extract energy from the chemical gradient between the vent fluid and the surrounding seawater. These microbes do not just live freely in the water around the vent. They live in mats on the rocks. They live in the gills and in the tissues of the larger organisms that have evolved to host them. They live in biofilms on every available surface, forming the biological infrastructure that makes all the rest of the vent community possible. Among the larger organisms that have evolved to exploit the chemosynthetic productivity of Indian Ocean hydrothermal vents, one stands out as perhaps the most remarkable animal discovered in any deep-sea environment anywhere on Earth. It is a gastropod, a type of snail, that lives in the specific vent environments of the Indian Ocean, and that has evolved a suite of anatomical features so extraordinary that when it was first described by scientists in 2003, it prompted an immediate and intense wave of biological, biochemical, and materials science research that has continued to this day. This animal is the scaly-foot snail, known formally as Chrysomalin squamiferum. And the characteristic that makes it unique among all known animals is its foot. In most gastropods, the foot is a muscular, fleshy organ used for locomotion. In the scaly-foot snail, the foot is covered on its sides and bottom with scales, hundreds of them, and those scales are made in part of iron sulfide minerals. The snail is literally plating itself in iron. Its scales contain a layer of gragite, an iron sulfide compound, that gives them their dark, metallic appearance, and that provides a degree of mechanical protection against the crushing force of the hydrothermal vent environment and presumably against the attacks of predators. Iron is not, under normal biological circumstances, used to make armor. Animals build hard structures out of calcium carbonate or silica or chitin or collagen, but not out of iron sulfide minerals. The scaly-foot snail appears to be unique in the animal kingdom in having evolved this strategy, and the question of how it manages to incorporate iron into its scales in such a controlled and organized way is one that has fascinated biochemists since the animal's discovery. The iron for the scales comes from the vent environment itself, from the iron-rich fluid that emerges from the vents and bathes the seafloor in dissolved metal compounds. The snail's biology has apparently found a way to sequester this iron and incorporate it into the mineral layers of its scales, essentially turning an environmental chemical into a biological raw material. The shell of the scaly-foot snail is also unusual. Like the scales, it has a layered structure, an outer layer of iron sulfide minerals, a middle layer of organic material, and an inner layer of the conventional calcium carbonate that forms the shells of most mollusks. This three-layered architecture turns out to be extraordinarily effective at absorbing mechanical stress and resisting cracking, so effective, in fact, that materials scientists have studied it as a model for the design of new protective materials. The snail's armor, in other words, has structural properties that human engineers find genuinely difficult to replicate, even with access to modern manufacturing technologies. In the darkness of the deep Indian Ocean, evolution has arrived at a materials solution that science is still working to understand and apply. The scaly-foot snail is found only in a few specific hydrothermal vent fields in the Indian Ocean. Its distribution is limited, its populations are apparently small, and its habitat is, by definition, dependent on the active venting of hydrothermal fluid, a process that can persist for years or decades, but that eventually ceases when the geological conditions driving it change. The snail has been classified as an endangered species, not because of direct human exploitation. It lives at depths far beyond the reach of any conventional fishery, but because of the potential future threat from deep-sea mining. The mineral deposits that accumulate around hydrothermal vents are rich in the same metals that are increasingly in demand for modern technology: copper, zinc, cobalt, and others, and there is growing commercial interest in developing the capability to mine those deposits at depth. The ethical and environmental implications of deep-sea mining in the Indian Ocean are complex and still being worked out by scientists, policymakers, and the international bodies that govern the use of the high seas. What is clear is that the deep seafloor, including the hydrothermal vent environments, is far more biologically rich and ecologically important than was understood even a few decades ago. The organisms that live at vents like those inhabited by the scaly foot snail have nowhere else to go. They are specialists in one of the most extreme environments on Earth, adapted over millions of years of evolution to the specific conditions of the vent. If those conditions are destroyed or even significantly altered by human activity, the organisms that depend on them cannot simply relocate to another habitat. They will be gone. This is a recurring theme in deep-sea biology: the extraordinary specificity of deep ocean life, the degree to which organisms have evolved to the precise conditions of their environment, makes them exceptionally vulnerable to any significant disturbance of that environment. The deep ocean is not resilient in the way that some more dynamic, high-energy ecosystems can be. It operates slowly, on energy budgets that are a tiny fraction of what surface ecosystems work with, and recovery from major disturbances, when recovery occurs at all, happens on timescales of decades to centuries. A mining operation that physically removes the mineral substrate of a vent field and disperses the sediment plume over a wide area of surrounding seafloor could potentially affect the biology of a region for generations. These are not hypothetical concerns. They are the practical scientific context in which every new discovery about the deep Indian Ocean is now being made. To find something new in this ocean, a new vent field, a new seamount community, a new species of organism adapted to the deep seafloor, is simultaneously to understand that what has been found has never had to survive human-caused disturbance before, and that it might not be equipped to do so. Let us move from the dramatic landscapes of the mid-ocean ridges to the vast, relatively flat expanses of the Indian Ocean's abyssal plains. These are the deepest and most extensive regions of the ocean floor, the true deep bottom, lying at depths of 4,000 to 6,000 meters across enormous areas of the ocean basin. The word plain is somewhat misleading, because the abyssal plains of the Indian Ocean are not perfectly flat. They have gentle undulations, occasional outcrops of rock, scattered fields of nodules and crusts, and the traces of ancient geological events preserved in the topography of the sediment surface. But compared to the dramatic relief of the mid-ocean ridges or the steep walls of submarine canyons, the abyssal plains are indeed relatively flat, a world of gentle gradients and enormous scale. The sediment that covers the abyssal plains of the Indian Ocean is one of the most scientifically valuable materials anywhere on Earth. It accumulates slowly in some areas, a millimeter per 1,000 years or less, as particles of various origins settle through the water column and come to rest on the seafloor. These particles include the remains of microscopic organisms that lived and died in the sunlit waters above, the calcium carbonate shells of foraminifera and coccolithophores, the silica frustules of diatoms and radiolaria. They include fine particles of dust blown from the continents by wind and carried out over the ocean before settling. They include volcanic ash from eruptions on the ocean floor or on nearby islands. They include cosmic dust, microscopic particles of extraterrestrial origin that fall continuously from space. And they include the products of chemical reactions in the water column and at the sediment surface. Each layer of sediment, no matter how thin, is a record of the conditions that existed at the time of its deposition. The species composition of the microfossils in a sediment layer reflects the temperature and chemistry of the ocean water at the time those organisms lived. The presence of volcanic ash layers marks the occurrence of specific volcanic events that can be dated independently and used to establish the chronology of the sediment record. The concentration of certain chemical tracers, isotopes of oxygen, carbon, and other elements, reflects the global climate state at the time of deposition, encoding information about ice volume, sea surface temperature, ocean circulation, and atmospheric composition in a form that can be read by geochemists using modern analytical techniques. A core of sediment drilled from the abyssal plain of the Indian Ocean is therefore a record of Earth's history, a continuous archive of environmental conditions extending back in time for tens of millions of years, with a level of detail and continuity that is unavailable in almost any other geological archive. Ice cores from ice sheets in Antarctica and Greenland provide similarly detailed records, but they extend back only a few 100,000 years at most, limited by the maximum age of ice that has not yet been compressed and lost to melting. Sediment cores from the deep ocean extend the record back much further, providing context for the recent climate changes recorded in ice at a level of geological history where ice simply does not exist. The information preserved in Indian Ocean sediment cores has been enormously valuable in reconstructing the history of the monsoon system, the seasonal reversal of atmospheric circulation that drives one of the most important and consequential weather patterns on Earth. The Indian Ocean monsoon is not just a regional weather phenomenon. It is a global-scale atmospheric feature that affects the distribution of heat and moisture across an enormous portion of the Earth's surface, and it has been operating in various forms for tens of millions of years, since well before the current configuration of continents and ocean basins existed. The history of the monsoon, as recorded in Indian Ocean sediment cores, is a story of variability, of oscillations between stronger and weaker monsoon states driven by changes in Earth's orbital parameters, by changes in the distribution of continental ice, by changes in the configuration of the continents themselves over geological time. During periods when the northern hemisphere received more summer solar radiation, driven by the regular, predictable cycles in Earth's orbital shape and tilt known as Milankovitch cycles, the temperature contrast between the Asian landmass and the surrounding ocean was enhanced, strengthening the monsoon circulation and driving more rainfall over the Indian subcontinent and the surrounding regions. During periods of reduced summer insolation, the monsoon weakened. These oscillations are recorded in the sediment through changes in the types and abundances of microfossils, changes in the concentration of wind-blown dust, and changes in the chemical composition of the sediment, all of them responding to the changes in atmospheric and oceanic circulation that accompanied the waxing and waning of the monsoon. Understanding the natural variability of the Indian Ocean monsoon over geological time is not merely an academic exercise. It provides the essential context for understanding how this critical weather system is likely to respond to the ongoing changes in global climate that are occurring today. The sediment record shows that the monsoon has responded in the past to changes in temperature and atmospheric composition, and it provides quantitative information about how sensitive the monsoon circulation is to those changes. This information is invaluable for climate scientists working to build and validate the computer models that are used to project future climate change and its consequences for the billions of people who depend on monsoon rainfall for agriculture, water supply, and basic survival. Beyond the sediment record, the abyssal plains of the Indian Ocean contain another archive of Earth history, the metallic nodules. These are concretions of iron and manganese oxides that form on the seafloor surface over millions of years, growing at rates so slow that they are essentially geological timekeepers. A typical abyssal nodule in the Indian Ocean grows at a rate of a few millimeters per million years, slower than the growth of fingernails by several orders of magnitude. As they grow, they incorporate into their layered structure trace metals from the surrounding seawater, including cobalt, nickel, copper, and rare earth elements, in concentrations that reflect the chemistry of the seawater at the time of growth. Manganese nodules are found scattered across vast areas of the Indian Ocean abyssal plains, not continuously, but densely enough in some areas to cover the seafloor with a pavement of dark, potato-shaped objects, each one a sphere or disk of mineral material, typically 5 to 10 centimeters in diameter, sitting on or just below the sediment surface. They are in their way beautiful. Their surface texture is smooth and rolling, their color a deep reddish brown or black, their internal structure, when sectioned and examined under a microscope, revealing layer upon layer of mineral growth like the growth rings of a tree, but stretched out over millions rather than hundreds of years. The chemical record preserved in manganese nodules is different from and complementary to the record in the sediment. While the sediment records the organic and inorganic particles that fell through the water column from above, the nodules record the chemistry of the bottom water itself. The cold, dense, oxygen-rich water that flows along the seafloor from high-latitude sources, slowly spreading through the deep basins of the Indian Ocean and eventually mixing with the overlying water masses. Changes in the chemistry of this bottom water over geological time are recorded in the chemical composition of the nodule layers, providing a record of how deep ocean circulation patterns have changed in response to the same climatic forcing that is recorded through different proxies in the sediment. Together, the sediment record and the nodule record provide a remarkably comprehensive picture of how the Indian Ocean has evolved over millions of years, how its temperature, its chemistry, its circulation patterns, and its biological productivity have all varied in response to the changing climate and changing geological configuration of the Earth. This picture is still being assembled, still being refined, with each new sediment core and each new chemical analysis adding resolution and detail to a story that was, only a few decades ago, almost entirely unknown. The bathymetric architecture of the Indian Ocean also includes a network of features that, though less dramatic than the mid-ocean ridges or the abyssal plains, are in some ways equally important for understanding how the ocean functions as a physical and biological system. These are the seamounts, underwater mountains that rise from the ocean floor but do not reach the surface, and the submarine canyons that cut through the continental margins, connecting the shallow coastal waters to the deep ocean interior. Seamounts in the Indian Ocean, as in other ocean basins, are formed primarily by volcanic activity. They may be the remnants of mid-ocean ridge volcanism, carried away from their point of origin by the movement of the tectonic plate beneath them and gradually sinking as the ocean crust on which they sit cools and contracts over millions of years. Or they may be the products of hotspot volcanism, the same type of fixed-point mantle plume activity that created the Hawaiian island chain in the Pacific, where a stationary source of magma in the mantle beneath has punched through the moving ocean crust repeatedly, building a chain of volcanic mountains that traces the path of the plate's motion over the hotspot. The Indian Ocean has several notable seamount chains, including the Reunion Hotspot Track, which traces the path of the Indian Ocean plate over the Reunion Hotspot from its present-day position near Mauritius back to the ancient flood basalts of the Deccan Traps on the Indian subcontinent. This chain of seamounts is not just a geological curiosity. It is a record of the movement of the Indian Ocean plate over the past 65 million years or so, and the timing of the seamounts along the chain can be used to calculate the velocity of plate motion and how it has varied over time. But seamounts are not just geological features, they are biological ones as well. The presence of an underwater mountain in the open ocean creates a local concentration of biological activity that is far greater than the surrounding flat seafloor or open water. The topography of a seamount forces the deep, nutrient-rich water that flows along the ocean floor upward as it encounters the obstacle of the mountain's flanks. This upwelling of nutrient-rich water fertilizes the sunlit surface layers above the seamount, driving enhanced phytoplankton growth and supporting an elevated density of marine life all the way up the food chain from microscopic algae to large predatory fish. The physical structure of the seamount itself, the hard rock surfaces, the complex topography, the current patterns created by the interaction of ocean flow with the mountain's shape, provides habitat for a diverse community of organisms, including deep-sea corals, sponges, and the many species of fish and invertebrates that associate with those reef-forming organisms. Deep-sea corals deserve particular attention in the context of the Indian Ocean's seamount communities, because they represent a class of organisms about which we knew almost nothing until quite recently, and about which there is still an enormous amount to learn. Unlike the shallow tropical corals that form the famous reef ecosystems of the Indian Ocean's coastal margins, the Great Barrier Reef, the coral reefs of the Maldives and the Seychelles and the Andaman Islands, deep-sea corals live in water that receives no sunlight whatsoever. They do not depend on the photosynthetic algae that live within the tissues of shallow water corals and that provide those corals with most of their energy. Instead, deep-sea corals are entirely heterotrophic. They feed by filtering organic particles from the water that flows past them, catching microscopic food items in the tiny tentacles that extend from each coral polyp. This makes deep-sea corals much more dependent on local current conditions than their shallow water relatives. They are typically found in locations where strong currents deliver a concentrated supply of food particles, locations like the flanks of seamounts, the edges of submarine canyons, and the tops of underwater ridges. In these locations, they can form extraordinary aggregations, dense forests of branching coral colonies that may cover large areas of the seafloor, and that in some cases can be centuries or even millennia old. Individual deep-sea coral colonies have been dated by radiometric methods to ages of thousands of years. Some are among the oldest living organisms on Earth, predating many of the trees in the world's ancient forests. The age of deep-sea corals makes them another kind of archive. Like tree rings, the growth layers in deep-sea coral skeletons record the chemical composition of the seawater in which they grew, and therefore, the climate conditions at the time of growth. Cores taken from deep-sea coral colonies in the Indian Ocean can potentially extend the record of ocean chemistry and climate into periods that are not covered by sediment cores or ice cores with the same level of resolution. They are, in other words, yet another page of the Indian Ocean's extraordinary geological and climatic record, a page that is still largely unread because the deep-sea coral communities of the Indian Ocean have been studied far less thoroughly than those in other ocean basins. The submarine canyons of the Indian Ocean's continental margins are among the most dramatic topographic features of the entire ocean basin and among the least understood. These are enormous gullies cut into the continental slope, the steeply inclined region where the shallow continental shelf gives way to the deep ocean floor by erosive processes that can include the flow of dense, sediment-laden water known as turbidity currents. Turbidity currents are among the most powerful sediment transport processes on Earth. They can travel at speeds of tens or even hundreds of kilometers per hour, carrying enormous quantities of sediment from the continental shelf and slope out into the deep ocean, where the sediment eventually settles and accumulates in deep-sea fans, thick piles of sediment at the base of the submarine canyon that can be among the most voluminous sediment deposits on the planet. The Indus Fan and the Bengal Fan, the enormous deep-sea sediment accumulations at the mouths of the Indus River and the Ganges-Brahmaputra River system respectively, are the two largest submarine fans on Earth, and both of them are features of the Indian Ocean. The Bengal Fan alone covers approximately 3 million square kilometers of the Indian Ocean floor north of the equator, and it reaches thicknesses of more than 20 kilometers in some places, an almost inconceivable accumulation of sediment that records not just the erosion of the Himalayan mountains over the past 50 million years or so, but also the tectonic history of the collision between the Indian subcontinent and Asia that created those mountains in the first place. The sediment in the Bengal Fan is, in a sense, the pulverized remains of the Himalayas, mountains that were pushed up by the collision of tectonic plates and then slowly ground down by ice and water and wind, and carried to the sea by the rivers that drain the subcontinent, and from there transported to the deep ocean by the processes of submarine gravity flow. The thickness and the composition of the sediment in the Bengal Fan have been used to track the timing and rate of Himalayan uplift, to understand the history of erosion in the mountain range, and to reconstruct the history of monsoon rainfall intensity, because the rate at which sediment is delivered from the mountains to the sea depends, among other things, on how much precipitation falls in the mountain catchments, and therefore on the strength of the monsoon. The Bengal Fan is, in other words, another archive, one of enormous physical scale, recording the intertwined history of tectonic uplift, climate change, and erosion over tens of millions of years in the deep sedimentary record of the Indian Ocean floor. The exploration of these deep sedimentary records is not just a matter of academic interest in Earth history. Understanding the Indian Ocean's past is essential for understanding its present and anticipating its future. The ocean's circulation, its heat content, its biological productivity, its chemistry, all of these are determined in part by the ocean's history, by the slow processes of sedimentation and chemical exchange that have been operating over millions of years and that have brought the ocean to its current state. Understanding how those processes have operated in the past, how the ocean has responded to changes in climate and geology, is the only way to build the kind of physical and biochemical understanding that allows scientists to make meaningful projections about how the ocean will respond to the changes that are happening today. The Indian Ocean is warming. This is not a statement about future projections. It is an observed fact established by decades of temperature measurements at various depths and locations throughout the ocean. The Indian Ocean has been warming faster, on average, than either the Pacific or the Atlantic over the past several decades, and this warming is having measurable consequences for the ocean's biology, its circulation, and its interaction with the atmosphere. The warming is affecting the intensity and timing of the monsoon. It is changing the distribution of marine species, as both predators and prey shift their ranges in response to changing temperature conditions. It is affecting the vertical mixing of the ocean, the exchange of water between the surface and the deep, in ways that may reduce the supply of nutrients to surface waters and thereby affect the productivity of the ocean's food web. Understanding these changes and placing them in the context of the ocean's much longer history requires exactly the kind of deep knowledge of the Indian Ocean's geology, chemistry, and biology that is being slowly and painstakingly assembled by the scientific expeditions we have been describing. The sediment cores that tell the story of past monsoon variability are essential for understanding how the current changes relate to the natural range of variability the system has experienced. The studies of deep-sea carbon cycling are essential for understanding the ocean's role in the global carbon budget. The investigations of deep-sea biology are essential for understanding the full extent of the marine biodiversity that is at stake. There is a quality to the Indian Ocean's deep environments, a quality that is hard to articulate without resorting to language that sounds more poetic than scientific, that has to do with time. The deep ocean operates on timescales that are largely incompatible with human experience. The circulation of deep water through the Indian Ocean basin takes hundreds to thousands of years. The accumulation of a centimeter of abyssal sediment takes thousands to tens of thousands of years. The growth of a manganese nodule from a tiny nucleus to the size of an apple takes millions of years. The geological processes that created the ocean basin, the rifting of Gondwana, the northward migration of the Indian subcontinent, the collision with Asia, operated over hundreds of millions of years. In the face of these timescales, human history, the entire span of recorded human civilization, is less than a single tick of the geological clock. Pyramids of ancient Egypt, the rise and fall of empires, the Industrial Revolution, the age of exploration, the entirety of everything we call history, all of it fits into a geological instant, a fraction of the blink of an eye by the standards of the processes that shaped and continue to shape the Indian Ocean. This is not a comfortable fact for creatures who experience time in years and decades. It requires a deliberate act of imagination to hold it in mind, to feel its full weight. But it is also, in a strange way, reassuring. The deep Indian Ocean has been here for tens of millions of years. It has survived enormous changes, changes in climate, changes in ocean chemistry, changes in the configuration of the continents. Life has persisted in its depths through all of it, adapting and evolving and finding new ways to extract energy and meaning from an environment that seems, by surface standards, impossibly hostile. The resilience of the deep ocean, its capacity to endure over geological time, is itself a remarkable fact, worthy of contemplation alongside all the specific discoveries of geology and biology and chemistry that we have been considering. This resilience, however, is not unlimited. And one of the most important things that the accumulating knowledge of the Indian Ocean's deep environments is teaching us is where the limits of that resilience lie, what the deep ocean can absorb and recover from, and what it cannot. The slow pace of deep-sea processes, which makes them so valuable as archives of Earth history, also makes them extraordinarily vulnerable to rapid disturbance. The organisms of the deep seafloor are adapted to stability, to the gentle, predictable conditions of the permanent midnight, where temperature and pressure and chemistry change only on geological timescales. Rapid changes on human timescales, whether from direct physical disturbance, chemical contamination, or the indirect effects of warming and acidification, are changes that the deep ocean's biology has no evolutionary experience in coping with. The abyssal plain communities of the Indian Ocean, the sparse but real communities of organisms that live on and in the sediment, feeding on the marine snow that drifts down from above, were subjected to a famous natural experiment in the 1980s when a research expedition deliberately disturbed a section of abyssal seafloor in the Pacific, and then returned periodically over the following decades to observe the recovery. The results were sobering. Decades after the disturbance, the disturbed area was still clearly distinguishable from the surrounding undisturbed seafloor. The biological communities in the disturbed zone had not recovered to anything approaching their original state. The deep seafloor does not heal quickly. It does not have the biological turnover rate, the energy supply, or the recruitment of new organisms from nearby populations needed to recover on timescales that human beings or human institutions would find meaningful. This experimental evidence, combined with the growing knowledge of deep-sea biodiversity and the increasing commercial interest in deep-sea mineral resources, creates an urgent scientific and ethical imperative to understand the deep Indian Ocean before it is disturbed by human activity. Every expedition to the deep floor of this ocean is, in part, a baseline study, an attempt to document what is there before whatever comes next. Every new species described, every new vent field mapped, every sediment core analyzed and archived is a record of what the Indian Ocean contained before the era of extensive human engagement with its depths began. The pace of discovery in the deep Indian Ocean has been accelerating over the past 2 decades, driven by advances in the technology of deep-sea exploration and by a growing recognition of the scientific and practical importance of understanding what lies beneath the surface of this enormous water body. Remotely operated vehicles, ROVs, have made it possible to visit the deep seafloor repeatedly and for extended periods without the limitations and risks of human-occupied submersibles. Autonomous underwater vehicles, AUVs, have made it possible to survey large areas of the seafloor at high resolution without the need for constant control from a surface ship. Advances in sonar technology, in underwater camera systems, in the tools of molecular biology that can extract and analyze genetic material from the most minute environmental samples. All of these have dramatically expanded the capabilities available to scientists working in the deep Indian Ocean. And yet the challenges remain formidable. The Indian Ocean is vast. Its deep environments are remote, physically hostile, and expensive to reach. The number of research vessels capable of conducting deep-sea work in this ocean is small, the time available for scientific expeditions is limited, and the competition for that time is intense. The result is that exploration proceeds slowly, in isolated expeditions that each add a piece to the puzzle, but that collectively still leave enormous gaps. For every stretch of seafloor that has been visited and documented, there are many times that area that remain essentially unknown. This is the fundamental paradox of Indian Ocean science in the current era. We know enough to know how much we do not know. We have seen enough of the deep ocean to understand that it is complex, biologically rich, geologically dynamic, and scientifically important, and that most of it remains beyond our knowledge. We are like explorers who have crossed a vast territory at night, seeing by the light of lanterns carried at arm's length, catching glimpses of what lies immediately around us while the vast majority of the landscape stretches away unseen in every direction. The analogy of exploration is not just rhetorical. It is literally accurate. The scientists who work in the deep Indian Ocean are explorers in the fullest and most rigorous sense of that word. They are going to places that have never been visited, observing phenomena that have never been seen, discovering organisms that have never been described. Every dive of a submersible or ROV into the deep Indian Ocean has a genuine probability of encountering something that science has not previously encountered: a new species, a new geological feature, a new ecological relationship, a new chemical process. This is not hyperbole. It is the straightforward consequence of the fact that most of the deep ocean has never been explored. The experience of discovering something genuinely new in the deep ocean, something that has existed in the darkness for millions of years without any human awareness of its existence, is one that scientists who have had the opportunity to do so describe in terms that go beyond the usual language of scientific observation. It is an encounter with the genuinely unknown in a world that most people assume has been thoroughly mapped and catalogued. It is a reminder that the Earth is still, in important ways, a frontier, that there are real discoveries to be made, real mysteries to solve, right here on our own planet. The Indian Ocean holds more of those mysteries than any other comparably large region of the Earth's surface. Its geological complexity, its biological richness, its role as a driver of global climate, its history as the cradle of ancient maritime civilizations, and the extraordinary depth of our ignorance about its deep environments. All of these combine to make it one of the most compelling and consequential subjects of scientific investigation in the world today. As we reach the midpoint of our exploration of this extraordinary ocean, let us pause to take stock of what we have learned and what we have yet to encounter. We have descended from the surface through the water column, understanding the physical structure of the ocean and the biological communities it supports at different depths. We have explored the geological history of the Indian Ocean basin, its formation from the breakup of Gondwana, the discovery of lost continental fragments like Mauritius, the mystery of the gravity anomaly, the dynamic landscape of mid-ocean ridges and abyssal plains. We have visited the hydrothermal vents, those extraordinary windows into a chemosynthetic world that operates entirely independently of the sun, and we have met some of the remarkable organisms, including the iron-armored scaly-foot snail, that have evolved to live in those extreme environments. We have considered the sediment record, that geological archive of millions of years of Earth history, encoded in the slow accumulation of particles on the abyssal plains. We have thought about seamounts and submarine canyons, about deep-sea corals and manganese nodules, about the Bengal fan and the monsoon. We have grappled with the paradox of knowing enough to understand how much we do not know, and with the ethical implications of that knowledge in the context of growing human activity in the deep ocean. In the second part of our exploration, we will go deeper into the specific details of how exploration happens, how scientists organize and conduct expeditions to the deep Indian Ocean, what it is actually like to descend to the seafloor in a research submersible or to operate an ROV from the deck of a research vessel in the middle of one of the most remote ocean basins on Earth. We will follow specific discoveries as they unfold, new vent fields, new species, new geological features, and we will trace the implications of those discoveries for our understanding of the ocean and the planet. We will consider the future of Indian Ocean science and what the growing urgency of environmental understanding might mean for how we invest in exploring and protecting the deep ocean in the years ahead. The Indian Ocean keeps its secrets well. It is dark down there and cold, and the pressure is crushing and the distances are vast, but the secrets are not impenetrable. With patience and technology and the kind of sustained scientific commitment that the discovery of genuine mysteries demands, they are yielding one by one to human curiosity and human intelligence. And each secret revealed opens the door to 10 more, the nature of genuine exploration in any frontier in any time. The floor of the Indian Ocean is a record of 4 billion years of Earth history. It is a catalog of life forms that evolution has produced under conditions we are only beginning to understand. It is a physical and chemical system of extraordinary complexity, interconnected with the atmosphere and the land and the organisms of the surface ocean in ways that we are only beginning to map. And it is, for now, still largely unknown, a frontier of science that stretches away in every direction from the narrow corridors of human knowledge that our expeditions have so far managed to illuminate. There is no more exciting place on Earth to be a scientist, and there is no more important ocean to understand. This has been part 1 of our exploration of the Indian Ocean. We will return in part 2 to continue this journey into the deep. We left our exploration of the Indian Ocean at a moment of recognition. The recognition that every discovery in this ocean opens more doors than it closes, that every answered question generates a constellation of new ones, and that the depth of human ignorance about this vast body of water is itself one of the most scientifically significant facts we can contemplate. In part 1, we traced the geological origins of the Indian Ocean, descended through its water column, visited its hydrothermal vents, met the extraordinary organisms that have evolved to live in chemosynthetic darkness, and considered the sedimentary archives that preserve tens of millions of years of Earth's climatic and geological history in the quiet accumulation of particles on the abyssal plains. Now we go further. We follow the scientists into the field, onto the research vessels, into the submersibles, down to the seafloor itself, and we trace the actual process of discovery as it unfolds in real time in one of the most remote and challenging environments on the planet. We examine the specific tools and methods of deep-sea exploration, the particular difficulties of working in the Indian Ocean, and the cascade of understanding that flows from each new piece of data, each new sample, each new image transmitted from the darkness below. And we confront directly and honestly the questions that the accumulating knowledge of the Indian Ocean forces us to ask about our relationship to the deep ocean, what we owe it, what it offers us, and what we stand to lose if we fail to understand it before we begin to exploit it. The story of the Indian Ocean is not finished. It is not even close to finished. But it is being written, expedition by expedition, discovery by discovery, in the work of scientists who have chosen to spend their careers in pursuit of one of the last great genuine mysteries on Earth. To understand what deep-sea exploration actually involves, what it takes, physically and logistically and intellectually, to conduct scientific research in the deep Indian Ocean, you have to begin with the research vessel. The ship is not merely a platform for getting scientists to the right location. It is a laboratory, a base of operations, a communication hub, a mechanical workshop, a data processing center, and a home for dozens of people who may spend weeks or months at sea without setting foot on land. A modern deep-sea research vessel is one of the most technologically sophisticated working environments in science, and the logistics of operating one in the remote waters of the Indian Ocean are correspondingly complex. Consider the planning that goes into a single deep-sea expedition. Months or years before the ship leaves port, scientists are working to identify the specific questions they want to answer and the specific locations they need to visit in order to answer them. This requires synthesizing everything that is already known about the target region, pulling together existing bathymetric data, previous expedition reports, published scientific literature, satellite observations, and any other relevant information, and using it to design a scientific program that makes the best possible use of the limited time available at sea. Ship time in the deep Indian Ocean is expensive, tens of thousands of dollars per day, and every hour must be used as efficiently as possible. There is no room for improvisation, for wandering around to see what turns up. Every dive, every sample, every survey track must be planned in advance with as much precision as the available knowledge allows. But of course, the available knowledge is limited. That is, after all, the whole point. Scientists are going to the deep Indian Ocean precisely because they do not know what is there. And this creates an inherent tension in the planning process. You must plan in detail for an environment about which you know relatively little, making decisions about where to go and what to do based on incomplete information, while maintaining enough flexibility in your program to respond to unexpected discoveries that may completely alter your understanding of the target region and the scientific questions worth asking. Experienced deep-sea scientists have learned to embrace this tension rather than fight it. They build flexibility into their programs, contingency plans for different scenarios, a hierarchy of scientific priorities, so that if the most important objective turns out not to be feasible, there is always a second and a third priority to pursue. They maintain a culture of rapid collaborative decision-making aboard ship so that when new data arrives, when the first sonar images of an unmapped area reveal an unexpected feature, when an ROV dive encounters an organism or a geological structure that no one was expecting, the scientific team can quickly assess what it means, discuss its implications, and decide how to respond. This culture of adaptive science is one of the things that makes deep-sea research simultaneously frustrating and exhilarating. Every expedition produces surprises. Not all of those surprises are welcome, whether that prevents operations, equipment malfunctions, oceanographic conditions that make a planned dive impossible, but many of them are extraordinary. Many of them are the kind of discovery that careers are built around, the kind of observation that ends up changing what everyone in the field thinks they know about the deep ocean. The technology of deep-sea exploration has evolved dramatically over the past several decades, and that evolution has transformed what is possible in the Indian Ocean and in other deep ocean settings. The earliest deep-sea observations were made by lowering instruments, thermometers, pressure gauges, water sampling bottles on long cables from ships, collecting data at specific depths without any visual information about what the instruments were passing through. These methods provided essential information about the physical and chemical properties of the water column, but they gave scientists no window into the biological and geological world of the deep seafloor. The first generation of human-occupied submersibles, developed in the mid-20th century, provided that window, but at enormous cost and with significant limitations. Human-occupied vehicles require life support systems, pressure hulls of extraordinary strength, complex navigation systems, and backup safety systems of every kind. They are expensive to build, expensive to operate, and limited in the time they can spend on the bottom by the life support endurance of their crew. A typical dive in a human-occupied submersible might last 6 to 8 hours from launch to recovery, of which perhaps 4 to 5 hours are spent on the actual seafloor. The crew, typically a pilot and 1 or 2 scientists, can observe through small viewports, collect samples with manipulator arms, and gather data with instruments mounted on the outside of the vehicle. But their ability to cover large areas, to make rapid decisions about where to go and what to investigate, is severely constrained by the limitations of the vehicle and by the very human need to surface before the oxygen runs out. Remotely operated vehicles, ROVs, changed this calculation profoundly. An ROV is an untethered or tethered robotic vehicle, controlled from the surface by a pilot watching camera feeds transmitted through a fiber optic cable. It does not require a pressure hull large enough or strong enough to protect a human crew. It does not require life support. It can, in principle, remain on the seafloor for as long as conditions allow, limited only by the endurance of the surface ship, the mechanical reliability of the ROV itself, and the available power supply. Modern deep-sea ROVs can dive to depths of several thousand meters, carry sophisticated sensor packages and sampling tools, and transmit high-definition video in real time to the surface ship, where a team of scientists can observe the seafloor environment in real time and direct the pilot to investigate features of interest. The experience of operating an ROV dive in the deep Indian Ocean is, in many ways, a communal one. The control room of a research vessel during an ROV dive is crowded and intense, the pilot at the controls, the navigator tracking the vehicle's position, scientists clustered around monitors showing different camera feeds and instrument outputs, all of them watching together as the vehicle descends through the water column and the seafloor gradually appears in the camera's lights. The moment of first contact, when the ROV's lights pick out the features of the seafloor after hours of descent through absolute darkness, is one that scientists who have experienced it describe as deeply affecting, regardless of how many times they have been through it before. The seafloor materializes out of the darkness like an alien landscape being revealed for the first time, which in many cases it literally is. The specific character of what the cameras reveal depends, of course, entirely on where in the Indian Ocean the ROV has descended. In some areas, the soft sediment plains of the abyssal floor, far from any geological feature of interest, the seafloor view is one of almost complete stillness. The sediment surface is smooth and undisturbed, extending away from the vehicle in all directions in a gentle, featureless plain broken only by the occasional small mound, the faint trace of a bottom-dwelling organism's path through the sediment, or the scattered dark disks of manganese nodules sitting on the surface like geological coins left on a table. Life is present here. There are organisms in the sediment, organisms on the nodules, organisms moving through the near-bottom water, but it is sparse and subtle, visible only when the cameras get very close. In other areas, on the flanks of seamounts, along the crests of mid-ocean ridges, at the edges of submarine canyons, the seafloor is an entirely different world. Hard substrate dominates, bare rock faces encrusted with organisms, fields of volcanic pillows and sheets, walls of mineral deposit, the skeletal frameworks of ancient deep-sea coral colonies. Life here is dense and varied, crowded onto every available surface, competing for the hard substrate that provides attachment points in a world where the sediment is too soft and unstable to support sessile organisms. The colors that appear in the ROV's lights are extraordinary, the deep reds and oranges of certain coral species, the white and yellow of others, the brilliant red of shrimp, the pale luminescence of fish that barely react to the unfamiliar light, creating a visual experience that is utterly unlike anything visible at the ocean's surface. And then there are the vents. The approach to an active hydrothermal vent system in the ROV cameras is unmistakable even before the vent structures themselves come into view. The water above an active vent field is warmer than the surrounding deep water, measurably warmer, detectable by the vehicle's temperature sensors, and it carries in suspension a faint haze of mineral particles that gives it a slightly milky appearance in the camera lights. The seafloor around a vent field is chemically different from the surrounding rock, stained by the minerals precipitated from the vent fluid, colored in shades of orange and yellow, and red by iron and sulfur compounds that paint the rocks in tones that seem impossibly vivid in the permanent darkness. And then the structures themselves appear, the mineral chimneys, some of them towering several stories high, their surfaces decorated with the dense communities of organisms that have colonized every available space in this chemical oasis. The shimmering distortion of superheated water around the active vent openings at the tops of the chimneys creates a visual effect like heat haze on a hot road, a mirage in the deep, and the plume of dark mineral-rich fluid rising from the most active vents creates a column of turbidity that is visible for tens of meters above the vent opening before diffusing into the surrounding water. Around the bases of the chimneys, the vent community is at its most dense and most diverse. Every surface is occupied. Tube worms extend their plumes from their tubes, filtering the vent-influenced water for the chemosynthetic bacteria on which they depend. Clusters of bivalves, the deep-sea relatives of clams and mussels, sit in tight aggregations wherever the chemical conditions are right. Crabs move through the community, feeding on whatever they can find. Fish hover at the edges of the vent's influence zone, reluctant to enter the hottest, most chemically extreme parts of the environment but drawn by the density of potential prey. And everywhere, coating every surface, living in the tissues of every larger organism, invisible to any camera but detectable by the chemical sensors and the genetic sequencing equipment in the ship's laboratory above, the microorganisms. The chemosynthetic bacteria and archaea that make all the rest of this possible. The process of collecting samples from deep-sea vent environments in the Indian Ocean illustrates perfectly the combination of technological sophistication and physical constraint that defines deep-sea science. The ROV's manipulator arms, articulated robot limbs capable of delicate or forceful movements depending on the task, are used to collect rock samples, water samples, sediment samples, and biological specimens, placing them in a suite of specialized containers designed to preserve them at the temperatures and pressures of the deep seafloor during the long ascent to the surface. Some organisms and fluids must be collected in pressure-retaining vessels that maintain the deep-sea pressure during recovery, because they would be destroyed by the rapid decompression that occurs during the normal ascent. Hydrothermal vent fluids, for example, contain dissolved gases and chemical compounds that would degas and escape if the fluid were brought to the surface without maintaining the pressure, like opening a carbonated beverage after shaking it, but at a scale and speed that would destroy the sample entirely. The organisms collected from vent environments present their own preservation challenges. Many of them are adapted to temperatures and chemical conditions that are difficult or impossible to replicate in a shipboard laboratory. Some will survive the ascent to the surface and can be kept alive in specially designed cold, high-pressure aquaria for at least a short time, allowing scientists to make observations and conduct experiments on living specimens. Others die during the ascent, their tissues collapsing or their biochemistry failing as the conditions of the deep are replaced by the very different conditions at the surface. Every sample, alive or dead, is immediately documented, labeled, subsampled for different analytical purposes, and either preserved or maintained in the most appropriate way available, depending on what measurements will eventually be made. The scientific analyses that follow the collection of deep-sea samples in the Indian Ocean span an enormous range of disciplines and methodologies. Geochemists analyze the composition of rock samples to understand the history of the ocean crust and the processes occurring in the mantle below. Biologists describe and catalog the macroscopic organisms, examining their anatomy, measuring their dimensions, preserving tissue samples for genetic analysis. Molecular biologists extract DNA and RNA from environmental samples, water, sediment, tissue, to characterize the community of microorganisms present, most of which are far too small to see and far too specialized in their nutritional requirements to be cultured in any standard laboratory medium. Physicists and oceanographers analyze water samples to characterize the chemical and physical properties of the vent fluid and the ambient deep water. Geologists examine the textures and mineral compositions of rock samples, looking for evidence of the geological processes that formed them and the history of fluid flow through them. All of this analytical work happens partly at sea, in the ship's onboard laboratories, and partly in shore-based research institutions after the expedition has returned to port. The data accumulate over months or years after an expedition, as different analyses are completed, and the results integrated with each other and with the existing knowledge of the target region. A single expedition to the deep Indian Ocean may generate enough scientific material to sustain a research program for a decade, producing a stream of publications that gradually builds a more detailed and more coherent picture of the specific environment that was visited. Let us consider in this context the specific story of how new hydrothermal vent fields are discovered in the Indian Ocean, because it illustrates the combination of careful planning, technological capability, and genuine good fortune that characterizes deep-sea exploration at its most exciting. The discovery of a new vent field typically begins not on the seafloor, but in the water column above it. Active hydrothermal vents inject enormous quantities of heat and chemically distinctive material into the deep ocean. This material rises from the seafloor in a buoyant plume, mixing with the ambient seawater as it rises and eventually spreading laterally at a depth where its buoyancy is exhausted, typically hundreds of meters above the seafloor. The resulting horizontal plume, sometimes called a neutrally buoyant plume, carries distinctive chemical signatures: elevated temperature relative to the ambient water, elevated concentrations of certain dissolved metals and gases, and anomalous concentrations of particles that scatter light differently than the surrounding water. Research vessels equipped with sensitive chemical and optical sensors can detect these plumes by towing instrument packages through the water at appropriate depths while surveying a target area. When a plume is detected, when the sensors register anomalies in temperature, particle concentration, or chemistry, the ship can trace the plume back to its source by surveying in a grid pattern and noting the direction in which the signal increases. This process, sometimes called fishing for plumes, is one of the primary methods by which new vent fields are located in the Indian Ocean, and it has guided the discovery of several important vent systems that were subsequently investigated by ROV or submersible. The first detection of a plume is a moment of heightened excitement aboard a research vessel. It means that somewhere below, perhaps a few hundred meters below the survey depth, perhaps more than a kilometer, there is an active vent system. The plume itself contains information. Its chemical composition reflects the composition of the vent fluid that produced it, giving scientists a preliminary indication of the type of geology and geochemistry at the source. The intensity of the signal gives a rough indication of the vigor of the venting. And the direction from which the plume comes, which can be estimated from the horizontal velocity of the deep current carrying it and the distribution of the signal across the survey grid, points toward the location on the seafloor that needs to be investigated. Once a plume has been detected and its probable source location estimated, the next step is typically a detailed bathymetric survey of the target area using the ship's hull-mounted sonar. This survey produces a high-resolution map of the seafloor topography in the vicinity of the estimated vent location, revealing the geological structure of the area, whether it is on the crest of a ridge, in a rift valley, on the flank of a volcanic cone, and identifying specific features that might be associated with active venting, such as volcanic cones, fault scarps, or the characteristic circular depressions that sometimes mark the sites of collapsed lava lake roofs. Only after the plume detection and the bathymetric survey does the ROV go into the water to actually look at the seafloor. And even then, the first dive may be exploratory, a survey dive covering a relatively large area at modest resolution to get an overview of the terrain and identify the most promising targets for more detailed investigation. Subsequent dives focus on specific features of interest, collecting samples and measurements from the locations that the survey dives have identified as most scientifically valuable. The Southwest Indian Ridge has been the site of some of the most significant hydrothermal vent discoveries in the Indian Ocean over the past 2 decades. This ultra-slow spreading ridge, running along the southwestern portion of the ocean basin, was long considered an unlikely candidate for active hydrothermal venting, because the conventional understanding of the relationship between spreading rate and hydrothermal activity suggested that very slow spreading ridges should have reduced magmatic heat supply and therefore reduced vent activity. The discovery of active vent systems on the Southwest Indian Ridge challenged this assumption and has led to a significant revision of the theoretical understanding of what drives hydrothermal circulation in different ridge settings. The vents discovered on the Southwest Indian Ridge have some characteristics that distinguish them from vents at faster spreading ridges. Because the magma supply is limited and the mantle rock is frequently exposed on the seafloor rather than being covered by volcanic basalt, the chemistry of the vent fluids is different, reflecting not just the interaction of seawater with hot volcanic rock but also its interaction with peridotite, the mantle rock that is unusually rich in certain elements, particularly magnesium, and that drives a different set of chemical reactions when it reacts with hot seawater. The biological communities at these peridotite-hosted vent systems are also different from those at basalt-hosted vents, reflecting the different chemical environment produced by the different rock type. One of the vent fields discovered on the Southwest Indian Ridge is remarkable for the extraordinary diversity of its mineral deposits and the complexity of its geological structure. The vent field sits at the intersection of several fault systems, in a geological setting where water can penetrate deeply into the oceanic crust and interact with rocks at high temperatures before emerging back at the seafloor. The mineral deposits it has produced over its geological history are correspondingly diverse: sulfides of copper, zinc, and iron, carbonate minerals, oxide minerals, a chemical complexity that reflects the complex history of fluid flow through the underlying rock. The biological communities associated with this vent field include species that are related to, but distinct from, those found at vent fields on the central Indian Ridge and in other ocean basins, suggesting that the vent communities of the Indian Ocean have their own evolutionary history, that they have been colonizing and evolving in isolation, in geological terms, for long enough to produce species that are not found anywhere else in the world. This observation has important implications for understanding how the specialized fauna of hydrothermal vents disperses and diversifies across ocean basins, a question that gets to the heart of deep-sea biogeography, the study of how life is distributed in the deep ocean and why it is distributed the way it is. The biogeography of deep-sea hydrothermal vent communities in the Indian Ocean is a field that has been developing rapidly over the past decade and a half, driven by the discovery of new vent fields and by the application of molecular genetic tools that make it possible to establish evolutionary relationships between organisms collected from widely separated locations. The fundamental question in vent biogeography is, how do the specialized organisms of one vent field get to another vent field? The vents themselves are isolated oases, islands of chemosynthetic productivity in a vast desert of cold, dark, low-productivity deep water. The distance between vent fields may be hundreds or thousands of kilometers. The specialized organisms that live at vents cannot survive in the open water between them. So how do they cross those distances? How do the founding populations of new vent communities get established at newly opened vent systems? The answer, as far as it is currently understood, involves the dispersal of larvae. Most of the larger invertebrate organisms associated with hydrothermal vents, tube worms, bivalves, crustaceans, reproduce by releasing tiny, free-swimming larvae into the water column. These larvae are carried by deep ocean currents, potentially over great distances, before eventually settling on the seafloor and developing into juvenile organisms. If they are fortunate enough to encounter a suitable vent environment, the right chemical conditions, the right temperature, the right substrate, they may successfully establish themselves and begin the process of building a new vent community. If they do not encounter a suitable environment within the time window of their larval phase, they die, and the crossing attempt fails. The probability of a successful crossing between vent fields depends on several factors: the distance between the vents, the speed and direction of the deep currents that carry the larvae, the duration of the larval phase of the species in question, and the presence or absence of intermediate vent fields that might serve as stepping stones. In the Indian Ocean, where vent fields are scattered along the ridge system, and the intervening distances are sometimes enormous, the connectivity between different vent communities is thought to be limited, meaning that populations at different vent fields are largely isolated from each other genetically, with limited exchange of individuals between them. This limited connectivity has important implications for conservation. If vent populations in the Indian Ocean are genetically isolated from each other, if each vent community is essentially an evolutionary island, then the extinction of a local population at one vent field is not easily reversed by recolonization from another vent field. Each population represents a unique genetic lineage, the product of potentially millions of years of isolated evolution in the specific environmental conditions of its particular vent. The loss of any one of these populations is the loss of something irreplaceable, not just a collection of organisms, but a unique evolutionary experiment, a unique biological response to the specific set of conditions that existed at that vent in the deep Indian Ocean. The connection between vent biogeography and the broader question of Indian Ocean biodiversity brings us to one of the most exciting and rapidly developing areas of deep-sea science: the use of environmental DNA, eDNA, to characterize the biological communities of the deep ocean without the need to physically collect individual organisms. Environmental DNA is the genetic material shed by organisms into their environment, fragments of DNA released into the water or the sediment from skin cells, mucus, feces, and decomposing tissue. By collecting water or sediment samples from the deep Indian Ocean and extracting and sequencing the DNA present in those samples, scientists can detect the presence of organisms that they might never actually see, organisms that are too small to be visible to cameras, organisms that were present in an area at a different time and left their genetic signatures in the water. Organisms that live in the sediment or in crevices in the rock and that would never be captured by conventional sampling methods. The application of eDNA technology to deep-sea exploration in the Indian Ocean is still in its early stages, but the preliminary results have been striking. Water samples collected during expeditions to the deep Indian Ocean have been found to contain DNA from an extraordinary diversity of organisms, many of them representing species that have never been formally described, species known only from their genetic sequences and with no physical specimens available for study. The molecular data reveal a deep-sea biological world that is far richer and more diverse than the conventional biological record the species described from physical specimens would suggest. This richness is not entirely surprising. The history of deep-sea exploration is littered with examples of extraordinary organisms discovered late, described incompletely, and understood only partially. The mesopelagic zone, the twilight zone of the water column, between 200 and 1,000 meters depth, is now known to harbor an enormous biomass of small fish, crustaceans, and gelatinous organisms that was almost completely overlooked until quite recently, partly because the nets and trawls used to sample this zone at night were far too coarse to catch many of the small organisms present, and partly because many of the organisms in this zone are transparent or nearly so, making them invisible even when they are present in large numbers. The application of acoustic methods, sending sound pulses through the water column and analyzing the echoes, revealed the true scale of mesopelagic biomass, which may be larger than the total biomass of all the fish in the ocean above it. The Indian Ocean's mesopelagic zone is one of the least studied of any major ocean basin, and the biological communities it contains are correspondingly poorly known. Recent expeditions have begun to address this gap, using a combination of net sampling, acoustic surveys, and eDNA analysis to characterize the organisms present at different depths and different locations across the basin. The picture that is emerging is one of remarkable diversity and of important variability. The mesopelagic communities of the Indian Ocean are not uniform, but vary systematically with geography, reflecting the underlying patterns of surface productivity, water mass structure, and oceanographic circulation that differ across the basin. The physical oceanography of the Indian Ocean, the patterns of water movement, temperature distribution, and chemical cycling that determine the physical environment in which all the biology takes place, is itself a subject of enormous complexity and scientific importance. The Indian Ocean is unique among the world's major ocean basins in one crucial respect. Unlike the Atlantic and Pacific, which have open connections to the ocean to both their north and south, the Indian Ocean is effectively closed at its northern end by the Asian landmass. Water can flow in and out of the Indian Ocean to the south through the passages between the ocean and the Southern Ocean, but to the north, the Eurasian continent blocks any through flow. This means that the circulation of the Indian Ocean must ultimately be driven by processes that are different from those operating in the other major basins, and that the response of the Indian Ocean to changes in climate forcing is fundamentally different from the response of the Atlantic or Pacific. The monsoon is the most important of these special forcing mechanisms. The seasonal reversal of the atmospheric circulation over the Indian Ocean, driven by the differential heating and cooling of the Asian continent relative to the surrounding ocean, creates a corresponding seasonal reversal in the near-surface ocean circulation. During the summer monsoon, the wind blows from the southwest, driving a surface current system that carries water from the western Indian Ocean toward the South Asian coast. During the winter monsoon, the wind reverses, blowing from the northeast and driving the surface circulation in the opposite direction. This monsoon-forced reversal of the ocean circulation is unique in the world. No other major ocean basin experiences a comparable seasonal oscillation in its near-surface current system. The consequences of the monsoon reversal extend deep into the Indian Ocean ecosystem. The seasonal change in wind direction and strength drives changes in coastal upwelling, the process by which wind-driven surface divergence pulls cold, nutrient-rich water up from depth to replace the water that is pushed away from the coast. During the summer monsoon, intense upwelling along the coast of Somalia and the Arabian Peninsula brings cold, nutrient-rich deep water to the surface, fueling a bloom of phytoplankton that supports some of the most productive fisheries in the Indian Ocean. During the winter monsoon, the upwelling ceases and a different circulation pattern prevails. The seasonal pulse of productivity driven by this upwelling is one of the most striking features of Indian Ocean biology, and understanding its variability, how it has changed in the past, how it may change in the future, is one of the central challenges of Indian Ocean science. The deep circulation of the Indian Ocean is driven by a different set of processes than the near-surface monsoon circulation. In the deep ocean, the dominant forcing is thermohaline, driven by differences in the temperature and salinity of water masses that determine their density and therefore their tendency to sink or rise. Dense, cold, salty water formed in the high-latitude Southern Ocean sinks and flows northward into the Indian Ocean basin, eventually filling the deep basins with what oceanographers call Antarctic bottom water, the densest water in the Indian Ocean, sitting on or near the seafloor and maintaining the cold temperatures characteristic of the deep ocean everywhere in the basin. Above the Antarctic bottom water, a series of intermediate and deep water masses occupy the middle depths of the Indian Ocean, each with its own characteristic temperature, salinity, and chemical signature, each carrying the fingerprints of the specific region and process that formed it. The movement of these water masses through the Indian Ocean is complex, influenced by the shape of the ocean floor, by the positions of mid-ocean ridges that act as barriers to deep flow, by the density differences between adjacent water masses, and by a variety of mixing processes that gradually blend adjacent water masses together as they travel through the basin. One of the most important consequences of the Indian Ocean's deep circulation is the transport of oxygen to the deep basins. The bottom waters formed at the surface in high-latitude regions and sinking rapidly carry with them the oxygen that surface water absorbs from the atmosphere. As these waters travel through the deep Indian Ocean, they gradually lose oxygen to the respiration of the organisms, primarily bacteria, that are decomposing the organic matter that falls continuously from the surface. In regions where the circulation is slow and the supply of organic matter from above is high, oxygen can be depleted to very low levels over wide areas, creating what oceanographers call oxygen minimum zones. The Indian Ocean has some of the most extensive and most intense oxygen minimum zones of any ocean basin in the world. These oxygen minimum zones are not biological deserts, although they might appear to be from a conventional perspective. They have their own specialized biology, organisms that have evolved to tolerate extremely low oxygen concentrations, or that have evolved metabolic strategies that allow them to live on chemical forms of energy in the near absence of oxygen, using nitrate or sulfate rather than oxygen as the electron acceptor in their metabolic reactions. The microbiology of Indian Ocean oxygen minimum zones is a subject of intense current research, because these organisms are not just biologically fascinating, they play important roles in the ocean's nitrogen and sulfur cycles, cycling these elements between different chemical forms and influencing the ocean's chemistry in ways that have global consequences. The nitrogen cycle in the Indian Ocean is particularly important and particularly unusual among the world's ocean basins. Nitrogen is the nutrient that limits biological productivity over much of the ocean, not because there is a shortage of nitrogen as an element, since the atmosphere is nearly 80% nitrogen gas, but because most marine organisms cannot use the nitrogen gas dissolved in seawater directly. They need nitrogen in the form of nitrate or ammonium, biologically available forms that are produced by the transformation of nitrogen gas through a process called nitrogen fixation, carried out by specialized microorganisms. The balance between nitrogen fixation, which adds biologically available nitrogen to the ocean, and denitrification, which converts nitrate back to nitrogen gas and removes it from the biologically available pool, determines how much nitrogen is available to support biological production over the ocean as a whole. In the Indian Ocean's oxygen minimum zones, denitrification proceeds at extraordinarily high rates. The bacteria that carry out denitrification thrive in the near absence of oxygen, converting nitrate to nitrogen gas as they decompose organic matter, and in doing so, they draw down the concentration of biologically available nitrogen in the water. This strong denitrification signal in the Indian Ocean influences the nitrogen balance of the global ocean, making the Indian Ocean one of the most important regions in the world for understanding the ocean's nitrogen cycle and its relationship to biological productivity and carbon cycling. The deep connection between the Indian Ocean's nitrogen cycle, its oxygen minimum zones, its biological productivity, and its role in the global carbon cycle illustrates the extraordinary interconnectedness of the processes operating in this ocean. Nothing in the Indian Ocean operates in isolation. The chemistry of the deep water influences the biology of the surface. The biology of the surface influences the chemistry of the deep. The circulation of the water, driven by climate and by the shape of the ocean floor, connects the different regions of the basin and links the Indian Ocean to the other major ocean basins through the global thermohaline circulation. The geological processes operating at the seafloor influence the chemistry of the water above. The organisms of the deep sea influence the chemical composition of the sediment that is accumulating beneath them. Everything is connected to everything else in a web of relationships so complex that it defies complete description and requires the combined efforts of oceanographers, biologists, chemists, geologists, and climate scientists to even partially characterize. It is this interconnectedness that makes the Indian Ocean so difficult to study and so important to study. The challenge is not simply one of access, of getting to the deep water and making measurements. It is the challenge of understanding a system of almost limitless complexity in which any measurement you make at any single location and any single time is only one tiny piece of a puzzle of enormous scale. The Indian Ocean is not a static object. It is a dynamic system, constantly changing on every timescale from seconds to millions of years, varying from one location to another, responding continuously to the forcing applied to it by the atmosphere above, the solid earth below, and the organisms within it. Meeting this challenge requires not just individual expeditions and individual measurements, but sustained, systematic observation programs, long-term monitoring networks that can track how the Indian Ocean is changing over time and provide the data needed to understand the causes and consequences of that change. The development of such monitoring networks in the Indian Ocean has been a major scientific priority over the past several decades, driven by the recognition that the monsoon, which affects the lives of billions of people across southern Asia and eastern Africa, is intimately linked to the physical state of the Indian Ocean and therefore requires sustained ocean observation for its long-term prediction. The Indian Ocean Observing System, known as INDOOS, is a network of moored buoys, autonomous profiling floats, tide gauges, and other measurement platforms distributed across the Indian Ocean and designed to provide continuous measurements of the ocean's temperature, salinity, currents, and surface meteorology. The data from INDOOS are transmitted in real time to meteorological centers around the world, where they are used as inputs to weather prediction and climate monitoring systems. The network has been in operation for several decades, and the data it has collected have transformed the understanding of Indian Ocean variability and its relationship to climate. But INDOOS, like all observing systems, is incomplete. The deep ocean, below 2,000 meters, is poorly covered by the current observing network. The biological and chemical dimensions of Indian Ocean variability are almost entirely uncovered by the existing observing infrastructure, which focuses primarily on physical measurements. And the remote southern portions of the Indian Ocean, far from any land and therefore logistically difficult to service and maintain, are among the least well-observed regions in the entire system. The development of autonomous underwater vehicles, AUVs, represents one of the most promising technological advances for addressing these observational gaps. Unlike ROVs, which are tethered to a surface ship and require a ship in constant attendance, AUVs are independent vehicles that can be programmed with mission parameters and then released to conduct surveys autonomously, without any real-time control from the surface. They navigate using acoustic positioning systems, inertial navigation, and in some systems, real-time adaptation to the environment based on the data they are collecting. They can dive to great depths, survey large areas at high resolution, collect water samples at pre-programmed depths, and return to a recovery point after completing their mission. For the Indian Ocean, AUVs offer a transformative capability. A single AUV deployment from a research ship can survey hundreds of square kilometers of seafloor or hundreds of thousands of cubic meters of water column while the ship attends to other activities, conducting other operations, maintaining station, or even transiting to a different location. Multiple AUVs deployed simultaneously can survey even larger areas, or the same area at different spatial scales simultaneously, providing a richness of spatial coverage that was previously impossible. And the data quality from a modern deep-sea AUV, the resolution of the sonar maps it produces, the accuracy of the chemical measurements it makes, the detail of the images it captures, is comparable to or better than what can be achieved from a surface ship with much more expensive and logistically demanding methods. The application of AUV technology to the deep Indian Ocean is still in its early stages, constrained by the cost of the vehicles, the limited number of platforms available, and the logistical challenges of deploying and recovering them in remote, rough seas. But the trajectory is clear. As AUVs become more capable, more reliable, and more economical, they will play an increasingly central role in deep-sea exploration and observation in the Indian Ocean and throughout the global ocean. The combination of ship-based exploration, for the detailed, high-resolution investigation of specific sites, with AUV-based systematic surveys, for the broad, comprehensive coverage that individual expeditions cannot provide, offers the most promising path toward the kind of basin-scale understanding of the Indian Ocean that scientists know is needed. Perhaps the most important intellectual development in Indian Ocean science over the past decade is not a specific discovery, but a conceptual shift, a change in how scientists think about the deep ocean as a system and about its relationship to the human world above. For most of the history of deep-sea science, the deep ocean was conceptualized as a remote, extreme environment, fundamentally separate from the world of human experience and interest, important for academic reasons, certainly, worthy of study in the same spirit that any mysterious and unstudied environment is worthy of study, but not urgently relevant to the practical concerns of human society. That conceptualization has changed profoundly. The deep Indian Ocean is now understood to be intimately connected to the human world in ways that make understanding it not just scientifically interesting, but practically urgent. The deep ocean is a major reservoir of the carbon cycle, absorbing and storing enormous quantities of the carbon dioxide that human activities release into the atmosphere. Changes in the deep ocean's circulation and chemistry, changes that are already occurring in response to climate warming, affect this carbon storage capacity and therefore feed back on the rate of climate change at the surface. The deep ocean's biological communities, including the organisms of the mesopelagic zone and the seafloor, play important roles in cycling carbon and other nutrients, and disrupting those communities has consequences for the entire ocean ecosystem, including the fisheries that provide food and livelihood for enormous numbers of people. The deep Indian Ocean is also a repository of resources that are increasingly being considered for extraction. Beyond the hydrothermal vent mineral deposits that we discussed in Part 1, the abyssal plains of the Indian Ocean contain vast quantities of manganese nodules, rich in cobalt, nickel, copper, and rare earth elements, that are of growing commercial interest as the world seeks new sources of the metals needed for the manufacture of batteries, electronics, and other technologies essential to modern life. The phosphorite deposits on some of the ocean's seamounts and continental margins represent another potential mineral resource. And the ocean floor sediments themselves may contain recoverable quantities of gas hydrates, ice-like deposits of methane locked in a solid crystalline structure by the combination of low temperature and high pressure that characterizes the deep seafloor that could potentially be used as an energy resource. The potential exploitation of these deep-sea resources creates an urgent need for exactly the kind of comprehensive baseline knowledge of the Indian Ocean's deep environments that science is still working to develop. Before any decision can be made about whether, where, and how to extract resources from the deep Indian Ocean, decisions that will inevitably be made at some point, given the scale of the global demand for the materials involved, science needs to know what is there, how it functions, and what the consequences of disturbance would be. This knowledge is still incomplete over most of the Indian Ocean, and the gap between what is known and what needs to be known before responsible resource management decisions can be made is one of the most pressing challenges in ocean science today. The governance framework for the deep Indian Ocean, the international legal and institutional arrangements that determine who has rights to the resources of the deep seafloor and who has the responsibility to protect the ecosystems that live there, is itself a subject of considerable complexity and ongoing development. The deep seafloor beyond the jurisdiction of any coastal nation, the area known as the area under international maritime law, is governed by the International Seabed Authority, a body established under the United Nations Convention on the Law of the Sea that is charged with managing the mineral resources of the international seafloor for the benefit of all humankind, while also ensuring the protection of the marine environment. The International Seabed Authority has developed regulations for the exploration of deep-sea mineral resources, and it has issued exploration contracts to a number of entities, national governments, state enterprises, and private companies for specific areas of the deep seafloor in the Indian Ocean and other ocean basins. These contracts permit exploration activities, the survey, sampling, and assessment of mineral resources, but not commercial extraction, which requires a separate set of regulations that are still being developed and debated within the international community. The process of developing those exploitation regulations is contentious because it requires balancing competing interests. The interest of countries and companies in accessing potentially valuable mineral resources against the interest of the scientific community and environmental advocates in protecting deep-sea ecosystems from potentially irreversible damage. The scientific community's position is clear. Exploitation regulations should not be finalized until sufficient baseline knowledge of deep-sea ecosystems exists to allow meaningful environmental impact assessment, and should include strong provisions for environmental monitoring, protected areas, and adaptive management in response to new scientific findings. Whether that position will prevail in the face of strong commercial and geopolitical pressures remains to be seen. What is certain is that the pace at which scientific knowledge of the deep Indian Ocean is being accumulated matters enormously for the quality of the decisions that will be made about the ocean's future. Every expedition that maps a new area of the seafloor, every biological survey that documents the communities of organisms living on or in the deep seafloor, every geochemical study that characterizes the chemical processes operating at or below the seafloor, all of it is building the knowledge base that will ultimately determine how well or how poorly the deep Indian Ocean's ecosystems are protected in an era of growing human activity. The scientists who dedicate their careers to studying the deep Indian Ocean are aware of this. They know that their work is not just intellectually valuable but practically consequential, that the data they collect and publish will be used, eventually, to make management decisions with real and lasting consequences for the ocean. This knowledge creates a sense of urgency that runs through the community of Indian Ocean scientists, a feeling that there is not enough time, not enough ships, not enough funding, not enough institutional support for the scale and pace of exploration that the current situation demands. And yet, alongside the urgency, there is also something else, something that is harder to quantify but equally real. There is wonder. The wonder of encountering the genuine unknown, of seeing for the first time landscapes and organisms that no human eye has ever seen, of making measurements that reveal the workings of systems that have been operating in complete ignorance of human existence for millions or billions of years. This wonder is not a soft or sentimental thing. It is the fundamental engine of science, the thing that drives people to spend weeks at sea in rough conditions, to work 20-hour days processing samples in a rolling laboratory, to sacrifice the ordinary comforts of a life on land for the extraordinary experience of being present at a genuine discovery. The scientists who are doing this work in the deep Indian Ocean are not, for the most part, famous. They do not appear on television or receive the kind of public recognition that might be accorded to scientists working on more immediately accessible problems. But they are doing something that will matter in ways that extend far beyond the scope of any individual career or any individual expedition. They are building, piece by piece, the knowledge of a world that most of human civilization does not know exists, a world of extraordinary complexity and beauty and biological richness, existing in permanent darkness at crushing depths, operating on timescales that make human history look like an eye blink. They are telling us, through the painstaking language of data and analysis, that the Earth is more interesting than we thought, that life is more adaptable than we thought, that the history of our planet is longer and stranger and more varied than our usual narratives of geology and evolution can easily accommodate. And they are telling us that there is more, vastly more left to discover. Consider the simple statistical fact. The Indian Ocean covers approximately 70 million square kilometers. Of that area, roughly 20% of the seafloor has been mapped at any resolution sufficient to reveal features smaller than 1 kilometer. The remaining 80%, some 56 million square kilometers, has never been directly surveyed. In that unmapped area, there are unknown seamounts, unknown vent fields, unknown biological communities, unknown mineral deposits, unknown geological features of every kind. The species that have never been described, the chemical reactions that have never been observed, the geological structures that have never been mapped, the sheer quantity of unknown knowledge embedded in that 56 million square kilometers of unexplored seafloor is almost incomprehensible. Every research vessel that travels across the Indian Ocean, every sonar system that pulses its sound downward through the water, every ROV that descends to the seafloor, each of them is reducing, in some small way, the scope of that unknown. Each of them is adding a line or a dot to a map that is still mostly blank. And each new line, each new dot, reveals something that changes the picture, adds a seamount here, a canyon there, a vent field in a location where none was expected, a community of organisms that has never been seen before. The seamounts of the southern Indian Ocean illustrate this accumulating knowledge particularly well. Vast, remote southern reaches of the basin, far below the roaring 40s where westerly winds drive the ocean into the most consistent and powerful wave systems anywhere on Earth. There are chains and clusters of underwater mountains that have been identified from satellite bathymetry, but that have never been directly visited by any scientific expedition. Their approximate locations are known. Their rough dimensions, how tall they are, how wide their bases, can be estimated from the satellite data. But their detailed topography, their geological character, their biological communities, all of this is completely unknown. In the few cases where expeditions have managed to visit seamounts in the southern Indian Ocean, fighting the weather, operating at the limits of what research vessels and their equipment can handle, the discoveries have been remarkable. Deep-sea coral communities of extraordinary density and diversity have been documented on the flanks of seamounts in this region, communities that have been accumulating for millennia in complete isolation from human activity, and that represent some of the most pristine examples of deep-sea reef communities anywhere in the ocean. Fish communities associated with these seamounts include species that are found nowhere else in the Indian Ocean, apparent endemics that have evolved in the isolation of this remote environment over geological time. And the geological features of the seamounts themselves, their mineral crusts, their sediment covers, the traces of ancient geological events preserved in their rocks, add to the record of the Indian Ocean's geological history. These discoveries are valuable precisely because the seamounts of the southern Indian Ocean have not been impacted by human activity, not by fishing, not by pollution, not by any of the myriad ways in which human civilization has altered marine environments elsewhere. They exist in something approaching their natural state, which means that studying them provides a genuine baseline, a picture of what deep-sea seamount communities look like in the absence of human influence. Baselines of this kind are increasingly rare in the ocean, as human activity has penetrated to ever more remote regions, and their scientific value is correspondingly immense. The theme of pristine baselines leads us to one of the most profound and emotionally affecting aspects of Indian Ocean science, the fact that we are, in many cases, discovering things just in time. We are finding communities of organisms, communities that have existed for thousands or millions of years in the undisturbed darkness of the deep, at exactly the moment when those communities are beginning to face threats from human activity. The scaly-foot snail, discovered in 2001 and formally described in 2015, was classified as endangered by 2019. Within 18 years of its scientific discovery, the species was already threatened by the potential expansion of deep-sea mining into its extremely limited habitat. This compressed timeline from discovery to endangerment in less than 2 decades is not unique to the scaly-foot snail. It reflects a broader pattern in which the expansion of human activity into previously remote environments is outpacing the scientific knowledge needed to manage those activities responsibly. Deep-sea trawling, which scrapes heavy nets across the seafloor to catch commercially valuable fish and invertebrates, has operated in parts of the Indian Ocean for decades, destroying deep-sea coral communities and other bottom habitats at rates far faster than those habitats can recover. The trawl fisheries often operated in areas where no baseline surveys of the seafloor communities had ever been conducted, where in many cases the communities being destroyed had never even been documented. The legal and institutional frameworks for protecting deep-sea habitats in the Indian Ocean have been evolving slowly, imperfectly, but in what most observers consider to be a generally positive direction. Some areas of the Indian Ocean high seas have been designated as areas of particular environmental significance, with restrictions on certain types of bottom disturbing fishing activity. Regional fisheries management organizations have developed measures intended to protect vulnerable marine ecosystems in the waters under their jurisdiction. And the discussions within the International Seabed Authority about exploitation regulations for deep-sea minerals have included serious engagement with the question of how to design environmental protections that are adequate to the scale of the potential impacts. But the gap between the protections that exist and the protections that scientific knowledge suggests are necessary remains large. Closing that gap requires both better science, more comprehensive knowledge of what is present in the deep Indian Ocean and how it functions, and better governance, more effective international mechanisms for translating that scientific knowledge into protective regulations that are actually implemented and enforced. In the context of all this complexity, the geological mysteries, the biological discoveries, the oceanographic complexity, the governance challenges, what is the most important thing to understand about the Indian Ocean? Perhaps it is this: the Indian Ocean is not separate from us. It is not a remote, alien environment that we can choose to engage with or ignore depending on our interests and priorities. The Indian Ocean is part of the same planetary system that we inhabit. Its climate is our climate, its carbon cycle is our carbon cycle. Its fisheries feed enormous numbers of people. Its monsoon waters the crops that sustain billions. The heat that it absorbs from the atmosphere moderates the temperature extremes that would otherwise make large parts of the globe uninhabitable. The oxygen that its phytoplankton produce contributes to the air that every living thing on Earth breathes. The Indian Ocean is not a background feature of our planet, a body of water over which ships travel and beneath which events proceed in irrelevant darkness. It is a fundamental component of the Earth system, connected to everything, influencing everything, responding to everything, and what happens to it matters in ways that extend far beyond the immediate concerns of marine science. This is why the exploration of the Indian Ocean, the patient, sustained, scientifically rigorous investigation of its depths and its history and its biology and its chemistry, is not a luxury or an academic indulgence. It is a necessity. It is the process by which humanity builds the knowledge needed to understand its own planetary home, to make informed decisions about how to use and protect the resources of this ocean, and to anticipate and respond to the changes that are coming as the global climate continues to shift. The technology that will carry this exploration forward is evolving rapidly. Beyond the ROVs and AUVs we have already discussed, a new generation of deep-sea exploration tools is being developed that will further extend human reach into the unknown depths of the Indian Ocean. Acoustic sensing technologies are becoming more sophisticated, allowing the detection and characterization of biological communities and geological features at distances and resolutions that were impossible only a decade ago. Deep ocean genomics, the analysis of genetic material extracted from deep-sea environments, is revealing the extraordinary diversity of microbial life in the deep Indian Ocean at a pace that is outrunning the capacity of taxonomists to formally describe and name the organisms being detected. Machine learning algorithms are being trained to analyze the enormous volumes of imagery and acoustic data being collected by deep-sea surveys, identifying features and organisms that human analysts would miss and accelerating the process of making sense of the data collected. Perhaps most significantly, the trend toward international scientific collaboration in Indian Ocean research is accelerating. No single nation's scientific community has the resources to explore and understand the Indian Ocean on its own. The ocean is too large, the questions too complex, the required diversity of expertise too broad. The great tradition of collaborative international oceanography, which has its roots in the mid-20th century and which produced some of the foundational knowledge of how the global ocean functions, is being renewed and expanded in the Indian Ocean context, with research programs that bring together scientists from many countries, research vessels from multiple nations conducting coordinated surveys, and data-sharing arrangements that make the results of individual expeditions available to the entire global scientific community. This collaborative tradition is one of the most admirable aspects of ocean science, and it is particularly important in the Indian Ocean context because the nations whose coastlines border this ocean, across southern Asia, the Arabian Peninsula, Eastern Africa, and the islands of the southern and equatorial basins, have a direct and vital stake in understanding and protecting the Indian Ocean's resources and environment. Building the scientific capacity of these nations, ensuring that they are not just the subjects of research conducted by scientists from outside, but active participants in the exploration and understanding of their own ocean, this is both ethically necessary and scientifically important. The Indian Ocean will be best understood and best protected by a global scientific community that includes the full diversity of human knowledge and perspective. Every so often, in the course of a deep-sea expedition in the Indian Ocean, something happens that crystallizes everything we have been exploring in this documentary into a single, irreducible experience. The cameras of an ROV are sweeping across the floor of an unmapped valley on an unexplored ridge, following the edge of a mineral outcrop when the image changes. Something appears that was not expected, something that the scientists in the control room have never seen before and cannot immediately identify. They call the pilot to stop the vehicle, to hold position, to bring the cameras in closer. The image stabilizes and sharpens, and what it shows, whatever it turns out to be, a new species, a new geological structure, a new type of chemical reaction visible in the colors and textures of the rock, is something that existed in the darkness of the deep Indian Ocean for millions of years without any human being knowing it was there. In that moment, something happens that is difficult to describe in purely scientific language. It is not just the accretion of data, the expansion of the knowledge base, the addition of another specimen to the catalog of deep-sea life. It is something more personal, more immediate, more emotionally resonant. It is the experience of being in the presence of genuine mystery, of standing at the edge of the known and looking into the unknown and finding there in the darkness something beautiful. The deep Indian Ocean is full of such moments, waiting to happen. They are waiting for the ships that have not yet been built, the scientists who have not yet been trained, the expeditions that have not yet been funded. They are waiting in the darkness of the abyss, in the mineral towers of the hydrothermal vents, in the sediment layers of the abyssal plains, in the ancient rock of the mid-ocean ridges. They are the geological secrets and the biological wonders and the chemical mysteries of a world that has been here for tens of millions of years, and that we are only now, at the very beginning of the 21st century, beginning to seriously explore. The story of the Indian Ocean is, ultimately, the story of what it means to live on a planet that is still, in important ways, unknown to us. It is the story of an Earth that is more complex, more dynamic, more biologically creative, and more geologically surprising than the simple categories of our ordinary experience would lead us to expect. It is the story of life finding a way in places where, by conventional understanding, life has no business being, in the superheated fluid of hydrothermal vents, in the crushing darkness of the abyss, in the oxygen-depleted waters of ancient ocean depths. And it is the story of human curiosity, patient, systematic, collaborative, humble before the scale of what it does not yet know, pursuing understanding into the most difficult and remote environments on the planet. There is still so much to discover. The gravity hole that bends the shape of the ocean's surface remains incompletely understood, its deep origins still being debated by geophysicists working at the frontier of mantle dynamics. The lost continent of Mauritius, buried beneath the Indian Ocean floor, has barely been glimpsed through the traces it has left in ancient zircon crystals on a distant beach. The biological communities of the deep seafloor, the mats of chemosynthetic bacteria, the forests of deep-sea coral, the communities of invertebrates that exist in total darkness at pressures that would crush any conventional technology, are documented in fragments, in isolated glimpses provided by individual expeditions to individual sites. The hydrothermal vents of the southwest Indian Ridge have been visited only a handful of times, and each visit has revealed new species, new chemistry, new geological complexity. The abyssal plains of the southern Indian Ocean, some of the most remote terrain on Earth, are almost completely unknown. The mesopelagic communities of the open Indian Ocean, the twilight zone organisms that mediate the flow of carbon from the surface to the deep, are known to be important for global carbon cycling, but are understood in only the most general terms. The sediment archive of the Indian Ocean floor, that continuous record of Earth's climatic and geological history stretching back tens of millions of years, has been read in scattered chapters, with vast stretches of the narrative still untouched. The work continues. Right now, as you watch this documentary, there are research vessels somewhere in the Indian Ocean, conducting some aspect of this great ongoing scientific investigation. There are scientists in shipboard laboratories analyzing samples collected from the deep seafloor. There are ROVs descending through the darkness toward the bottom of unexplored ridges. There are AUVs surveying seamounts that have never been mapped at high resolution. There are sediment cores being split and sampled in the cold laboratory of a research ship, their layers of mud and shells and mineral grains preserving, in their chemical composition, the memory of climates and oceans that no human being ever witnessed. And there are moments of discovery, quiet, patient, unhurried, but profound in their implications, happening every time a new piece of the Indian Ocean story is revealed. A new species identified from the genetic sequences in an environmental DNA sample, a new feature mapped by the sonar of a passing ship, a new chemical reaction understood from the composition of a vent fluid, a new climate event reconstructed from the isotopic composition of microscopic shells in a sediment core. Each discovery is small by itself. Together they are building something immense, a comprehensive understanding of one of the most important and least known regions of our planetary home. The Indian Ocean is not waiting for us. It has its own agenda, its own rhythms, its own purposes, or rather it has no purposes because it is not a purposeful entity but a physical and chemical and biological system operating according to the laws of nature, indifferent to human observation, unaware of human curiosity. But it is there, it has always been there, and it will be there long after the last human expedition has returned to port and the last measurement has been made and the last paper has been published. What we choose to do with the time and the technology and the understanding that we have, how seriously we take the responsibility to explore this ocean, to understand it, to protect it, will say something important about what kind of relationship we want to have with our planet. Not just with the Indian Ocean, but with all of it, with the whole extraordinary, complicated, mysterious, beautiful, fragile Earth that is the only home we have. The Indian Ocean keeps its secrets in darkness, in depth, in distance, in the slow patience of geological time. But it has been keeping those secrets for long enough. The tools are in our hands, the questions are before us, the discoveries are waiting in the deep. It is time to go further. It is time to look harder. It is time to listen with every instrument of science and every faculty of human curiosity to what this extraordinary ocean has been trying to tell us all along. The seafloor rises and falls with the slow breath of the earth. The water moves in patterns older than our species, driven by forces that were operating long before the first human being stood at the edge of the sea and looked out at the horizon with wonder. Beneath that horizon, beneath the surface that catches the light and the wind in the eye, the Indian Ocean holds its world in permanent darkness, alive, dynamic, complex beyond full comprehension, and absolutely essential to the health and stability of the planet we share. We have been exploring it in this documentary for 2 hours. Scientists have been exploring it with ships and instruments and extraordinary ingenuity for decades. And the ocean has been here, quietly accumulating its record of Earth's history, quietly sustaining its communities of extraordinary life, quietly doing what oceans do, connecting, cycling, absorbing, releasing, warming, cooling, breathing in its slow, planetary way for tens of millions of years. The distance between what we know and what there is to know is still enormous, but it is shrinking. Expedition by expedition, measurement by measurement, discovery by discovery, the darkness is retreating just a little. And in the space that opens as the darkness retreats, the Indian Ocean reveals itself to be more extraordinary, more important, and more worthy of our attention and our care than even the most optimistic scientist would have dared to predict. This is the Indian Ocean, Earth's last great mystery, and we are only beginning to understand it.